Okay, so we're live again. Hopefully everyone can see me okay. So welcome to the Express AI live stream, a weekly live stream we do where I do whatever it is I feel like doing at that time. Usually it's ExpressAI related or vector engine related. Yeah, this time it's going to be a bit of both, right? So essentially we're back in, like my vector engine machine, and we've got Tinygrad kind of working, and the idea is we're going to try and make this better. So just ahead of the stream, I tried a bunch of optimizations. There's a lot of optimizations you can turn on in the NEC compiler. But I tried a few just to see if there was any real difference, like if there was anything that was a major bottleneck in terms of the flags, and it doesn't look like there are. Like we can get like more flops by disabling most of these flags. So and by more it's like 0.5 gigaflops more, so it's nothing special. And yeah, so the idea is today I wanted to spend a little time trying to optimize it, see if we can make it better. Essentially, we know it can do better, right? One is we know that the vector engine should have 5 teraflops, right? Like that's the max that it can do, and we're at 1% of that. We also know that the average vector length that we're using is 35, which is not ideal, and the average vector op ratio is 55%. So this needs to be like 99, and that needs to be 256. That's what we want. As long as we have those things going, then we know like we're reaching the limits of the vector engine, and then it becomes a thing of, okay, how much time are we spending loading? Can we prefetch stuff? Can we make more things fit in the L1 and things like that? That gets a lot more complicated. But at least in the beginning part of the stream, I wanted to, look at the generated C++, see if there's something we can do to optimize it a little bit better for this particular hardware. And later, I also wanted to give training a model on this a try. So I'm a fan of the RWKV model, the RWKV model. It's a recurrent one, and I kind of like that idea for many different use cases. So we'll be taking the version of it that exists already for Tinygrad, RWKV v4, and there was recently a like tiny RWKV that was like a modification of version 5 that's simplified a little bit, and we are going to try to port that into this one and train it and see how well it goes and compare it to the other thing. So just to a lot more people than usual. So I think I'll start with a little bit of vector engine stuff, right? So just so that everybody here who's joining can be on the same page. So let me look at the vector engine wiki chip so we can see what I have going on here. Yeah, so this is the SX Aurora microarchitecture, and essentially if we go down here, you can see it's a 8-core machine where each one of these cores have this SPU and VPU, and the VPU has 32 vector processing elements, each one with 2 or like 3 FMAs, I think, that they can do all at once. And this is a super scalar out of order CPU, so you don't have to like manually draw up an Excel spreadsheet of the dependencies and try to get the ports to align and reorder your instructions. You don't have to do that stuff. In general, as long as you can make it more or less efficient, it'll figure out how to do it. So it's quite nice in that sense. And the main special sauce about it really is this vector processing unit and the fact that it has vector instructions. So let me go over the architecture guide real quick, which you can get in the thing. But essentially, let's make this a little smaller. And I'm using a new format today, so if anybody has any issues, like if I'm too loud or anything like that, please let me know. But yeah, essentially, you have instructions that operate on vectors. They have a vector length field. Let's see if I can find a good example of that. So you have your operation in the thing, and then you have like places for the vector register X and Y, and there's more. There's Z as well. And yeah, essentially the idea is you can say you have your vector registers are 256 elements long, and you can set your vector length to be 50 or 3 or 256. And what we want to do is make it always be 256 and then kind of get those into the pipeline. And the idea is when you give a 256 vector length in here, these are all going to be working at full tilt. If you have only 32, each one will do their one instruction, but they actually have the ability to do 2 more FMAs than you would normally do. So yeah, it's a interesting thing. This is, for those who know, this is like the Cray supercomputer type of instruction architecture. So very different than a GPU. And because of that, essentially, we can take the C code that is generated by Tinygrad and just compile it. And, it doesn't have terrible performance. It has just not great performance, right? Whereas if you were to do the same thing on a GPU, the performance would be abysmal, right? It would be absolutely crap if you were to do what we're doing right now on a GPU. So it's an interesting kind of architecture that we have going on here. So so I have a few questions on like how much we're actually using the cores and stuff, because each one of these cores is capable of I think 614 gigaflops. Yeah, something along those lines. 614 or 607, one of the two. I think it's 614 gigaflops each one. So yeah, we should I should make a seat of some sort on my computers. But yeah, so what was I saying? Yes, we have 614 gigaflops in each one of these cores. And in the latest one, we are getting 4 gigaflops. So, it could be possible that we're just doing everything on a single, like a single core. Now you can do some things to automatically make it multi-core, like this, and it's mainly this one, M parallel. When you have M parallel specified, it means when you have a for loop, it will try to automatically parallelize that for loop the same way you would kind of parallelize it with OpenMP. But yeah, so if I turn all this off and try it again, if we get more or less the same speed, then that means maybe we're only using one core and we need to look into using more. Because there's a few interesting things when it comes to just using this, because each vector core has this last level cache, which is 2 megabytes, and it's pretty big. And they also have their L1. So even if you are like using this vector core as efficiently as possible, right, generating your vector instructions always using 256 vector lengths, it's not going to really get that 614 gigaflops of performance unless everything really neatly fits into the LLC, right? So yeah, that's a kind of problem there. But anyway, we can see that there's problems, right? Like there's multiple store conflicts, unpacked loop on target type, unvectorizable dependency, all sorts of things, right? Like there's many issues with the code, that should go away. But yeah, look at that. We got 5.54 gigaflops here. And 5.6 gigaflops now. And that's faster than it was before. And I turned off the multi-cores. So, unfortunately, you won't see it if you do it this way, right? Like everything shows 99%. And that's just the way it is. But yeah, unfortunate. But we can at least see how much memory the thing's using in here and whether it's using anything at all. So yeah, it looks like we don't have to do parallel stuff right now. Although maybe this could be parallelizing. Let me try to get rid of all the M parallel things. Make sure OpenMP is false. Yeah, I think that's pretty much should be all the auto parallelization stuff. You can see our real min flops, 3.8 gigaflops happening right now. This is calculating 5.6, so close enough, I think. Let's try that again and see how that goes. But anyway, if we are able to use multiple cores, we just have a lot more LLC to use, right? And since each one is 2 megabytes, and this bandwidth here is 3 terabytes per second or so, it can be pretty good, right? On top of the fact that the HBM2 is a 1.5 teraflops or terabytes per second bandwidth as well. So yeah, should be pretty good. And yeah, you can see the ones that I'm using right now should be this one. It's the 10B, the one that I'm using. So we should expect 4.30 teraflops if we're doing 32-bit floats. I don't think I have a 10A, which has the highest bandwidth, but I also have VE 2.0s, which I think are up here, about this, but with a little bit more bandwidth. Which the other machine, I have two, if you noticed in the picture. Let me bring the picture back. So I had my video, and I can't, let me go to the brand thing. Overlay, yeah. So if we look at, my server here, one of them is a VE 2.0, and then the other's the VE 1.0 that the server came with. So we can play around with those, see how that works. So let's go back and look at what we're doing. 5.6 gigaflops. So that looks okay. Let's start looking into some of these things. So let me delete these reports. And then look into it. In our last stream, Paul also mentioned doing things without NLCPy. And he did get that working. The good thing about that is that once you've compiled that kernel, it'll always reuse it, right? So in here, every time I run it, I'm going to incur the cost of recompiling everything. But that's not necessary. It's just a quick shortcut. And for me right now, because I'm going to be playing around with things, I kind of prefer that it recompiles every time. So I'm going to do that. Okay, so let's look at what we're at. So our real MFlops, we got like 5.6 gigaflops. So that's faster than the CPU. That's good. But our vector length is 44. We have the 60 vector out ratio. We are spending 5 seconds in cache L1 cache misses. and 22 seconds in vector loads. The LLC hit element ratio is 95%, which is, pretty decent, I would say. And yeah, this we can't trust. It's not real, unfortunately. So we're always going to be using 8 threads, just because of the way it was, how the offloading is implemented. So useless. But yeah, I think there's the main thing is we should look at the average vector length. That should be something we could possibly really optimize. Ooh, a good question. So does the model fit into 48 gigabytes of VE memory? So the model that I'm going to train is our really, really small one. The reason why I like RWKV is that it's really good, even though it's very small. So with a 3 billion model, it's pretty good. And I think that has some interesting use cases. Memory size used 24 gigabytes. Non-swappable memory used 10 gigabytes. Yeah, so everything fits. And when it comes to the memory, the interesting thing is it's using the same memory APIs that you get in Linux and Unix. So, it will automatically swap. It has a whole virtual memory system, like you would expect. So, yeah, it can use swap, but in general, your allocations can fail if you run out of memory. And I kind of prefer that over swapping. But you can actually use the host memory as like a swap space. That's called heterogeneous memory. And not only can you use the host memory if you are running it inside the MPI cluster, you can actually use other host memory as well. So yeah, but anyway, this is just mainly saying that there's 10 gigabytes of memory that were pinned, and the total memory that we used was 24 gigabytes. So, when it comes to this training, there's a couple of parameters here. Like one's the batch size of 32. This suggests that I could use a 64 batch size and get even better performance. And I think that was the case. I did try 256 once, and that was no good. We can try that. I did a bunch of runs, so there's a lot of reports to delete. So let's give that a try. Okay, so I'm going to set this to 64. And if we run that, we'll start seeing a bunch of reports. So if we look at some of these, let's look at the different diagnosis errors. So it says vectorized loop, fuse, multiply, add. This looks like it was pretty good, right? So like this is more or less what you want to see. It's just a big V from here to here. And nothing inside that messes it up. So that's good. That's ideal. That's what you want to see. And then we see overhead of loop division is too large. So that must mean that it's like a very small loop or something. And then the multiple store conflict. So these are the things we kind of want to get rid of. And yeah, so I think these have been fused. So I added, fused, multiply, add. These all become fused, multiply, adds. And let's look at this one. We said overhead too large. 113, and then partially vectorized loop. This is what you don't want to see, because essentially it means that you're generating branch instructions, right? Loops in your assembly code. And you don't want that with the vector engine. You want to not have any loops in your code. It's just, well, ideally, but you're always going to have some loops. But anyway, so let's look at the partially vectorized is S, and then 113 is here. So it really doesn't like this, which is weird because I would expect this to be what it doesn't like, but it doesn't like this. So one thing you'll notice is there's these kind of groups of 4, like something plus 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, right? So Tinygrad is doing this. It's kind of assuming that we want to unroll things by 4 and then do that. And that's something that will work for SIMD, but we don't have a SIMD machine. If you want 4, you set your vector length to 4, and then you just have loop, and then that will work, right? So this is kind of like, not ideal, I think. And if I'm not mistaken, I'm guessing it's just saying that we're accessing this here too much, and that's a problem. And this is the thing that in the last live stream we kind of noticed and wondered, is there a way to get rid of that? And maybe there is. So let's try looking for that. Let's see, is there +3 around here? SMPi, that's Rockham stuff. Metal Mac. Okay. So these are an extra thing. I wouldn't mind seeing this and trying it out. Let's actually do that. So one of the interesting things of here is there's this extra folder with the GEMM, and it has, different GMMs, and then it calculates the flops that you get. So if we go to extras and possibly do go to GMM, Python, let's do CPU equals 1, GMM.py. I'm way too used to the Fortran at this point. Okay, so we can see, it's like a very quick kind of thing. And I wonder what we would get if we do a vector engine version of this. So let's copy GMM and pi and put VE, let's do NLC pi gmm.py, and then copy gmm.py to vegit gmm.py. So let's look at NLC pi 1 first. So for this one, we'll just do NLC pi as MP, and then run that. So do VE equals 1 Python NLC pi gmm. And we don't have data, so let's not do that. Yeah, so this is kind of what you would mainly expect. So you can see the CPU gets 100 gigaflops per second. That's ideal scenarios for a 24-thread CPU. I only have one CPU in this thing. And with the vector engine, we are getting 3 teraflops per second. Should be able to do a little bit better. Let me actually do number equals 1. And with the VE 2.0, you can see we're in the 4s. Right? So we got 4.1, things like that. So that's good. That's what we want. Okay, now let's go to VJIT. Yeah, I don't care about writing this out, so let's do that. And we want to do this with tensors. Do they not have a... I'm guessing it's this one, right? Map. No. Let me see if they have a Tinygrad implementation of that. That's not one. MetaConf. Tinygrad tensor. Let me do our tiny bits. What we want is a GMMN. TVM. Print source. Not too familiar with this one. It's weird. He doesn't have like GMMM implemented in Tinygrad. A little weird. I don't know. Let's do it this way. Okay, so let's go start with the torch ones. Torch one is the same, right? 512. Yeah. Let's only do float 32s. Right. And instead of torch, we'll be doing Tinygrad. Put Tinygrad types dot float 32. This is one of the things that's kind of unfortunate with the vector engine is that the SPU has implementations of 8-bit, 16-bit, 32-bit, 64-bit, and 128-bit floating point values. So these ALUs can do all of those things. The VPU is only able to do 32 or 64. And because it's an like a what's it called, like supercomputer type of architecture, that kind of makes sense, right? In general, when it comes to the big simulations, everybody's always using FP64, and it turns out that in deep learning you don't need FP64, and everything's just better if you go lower, for very interesting reasons. But yeah. Unfortunately, this doesn't have an easy way to do 16-bit floats on here. There is a way to use brain float 16. Kind of. The main thing about the advantage of using brain float 16 on the vector engine is that you can fit more data into your level 2 and level 3 cache because it'll be in there. You waste one of your kind of instructions masking things out, or masking and then shifting things. But otherwise, like because you're saving time from memory stalls. It can actually be a little bit faster using BrainFloat 16, but it's still using 32-bit computations. So yeah, it's an unfortunate thing. But the latest version, VE3, is able to use BF16 and FP16, and that's great. I wish I had one. But anyway, what we want to do this. Let's get rid of that NumPy in there. And okay, so we'll do for each one of these, we'll create that instead of torch rand. I want to do the Tinygrad version of that. If it would, that would be great. Torch from NumPy. Okay. Simple map home. Here we go, tensor rand. Okay, so that's good. So let me put that there, give ourselves some space. And we want the GMM. Okay, so let's go. Is this right? Types, and then we'll do d types dot float 32. The only one we'll support. We'll do this, although it might be interesting to see what the float 64 is. Okay. And then instead of torch.rand, we do tensor.rand dtype. And then we call .realize. And we do the same thing here, tensor.rand, CUDA realize. And then our torch prog, let's just call this prog. It's not a torch one anymore. Is equal to b@c torch.CUDA synchronize. We don't need to do that, I don't think. Well, we'll see if the numbers are kind of crazy, then yeah, we do need to do that. And that could be it. So if we do so if we do it this way, where we specify BE equals 1, this should still use the NLC Pi backend. That's a little different. We can see we are doing, what's this? That's way too many. I need to synchronize. Do we need to synchronize? Let's do a NumPy question. Yeah, so that looks a little weird. Let's also try the VEJIT one. So let's see if that works in the first place. That's 147 gigaflops. Okay. 1 teraflop, 9 teraflops, no good. And the fact that they're like the same for float and double means that we're probably not measuring anything worthwhile. So let's do it this way, that way, do it this, and then we are not using A. Since we're not using A here, now I'm not sure what this is going to do. Let's try that. Yeah, I wish I can get that many moles. It's gigaflops, right? Yeah, that is gigaflops. Too many gigaflops. Okay, this is simple net mole. Let's do that. Let's get this because I want it to be this thing. This is what I want. So let's do the same kind of thing. So n is equal to 512. Then if name equals main, they say that Java is hard. Okay, so our A will be tensor rand d type z type dot float 32, and that will be A, right? And then B will be a tensor rand d type is float 32. And our flop is equal to 2 times n times n times n, and for I in range 10, and we use start time as time dot monotone. C is equal to A at B transpose. End time is time dot monotonic. S is equal to ETST. And then we'll just print this line. One line too many. Okay, so we do this. D type's not defined. D types. Okay, so now that makes a little bit more sense. We're not seeing anything though. Let's do this for 100. Try that again, and then do the prog int equals detail, just to make sure we're using the vector engine. Average vector length 248, so that's pretty good. And we're doing it 100 times, and it's just really fast, right? So let's 1024. It should take. Okay, it doesn't take any time. Times 8. It's 3 gigabytes of RAM. This one still taking more or less the same, but our calculation is way up. Let's keep that at 512 and make this back to 10. I'm not seeing compiling happening though, which I was expecting to happen. We do this and then just do VE equals 1. We get more or less the same. That's not. Let's do the NLC pi with prog in equals detail. Okay, so what do we get with NLC pi? Good things, good numbers. Interesting thing, this 1 teraflop is kind of similar to what we get in Tinygrad. Vector op ratio. The megaflop's real number is strangely off. Vector op ratio. Yeah, we're hitting the cache 99% of the time, so yeah, it makes sense. And our hybrid vector length is 248, which is about what you'd expect. What happens if I do float 64 here? Seems very similar numbers, which could be a thing. It's not ideal. Essentially what it means is that the vector length is 256. It's not 512 when you're using 32-bit floats. It's still 256. So you have to use packed instructions. You kind of do like multiply upper and then multiply lower, and then those work. And if you use those, then you get double the performance. But if you don't use those, if you don't use them, you're not going to get any more performance than what you get for the 64-bit. But it's like strangely too high to get 4 teraflops. The MOPS are now, that's saying 5 here, 5 there. Vector length is that. Which is that. That's interesting. So let's go back to the VE JIT MMM and use VE equals 1. And getting a teraflop is pretty good, I would say. I mean, I wouldn't complain. But something's not right. Like you can look at the output here, we have like M flops real, right? And then here we have M flops real 0. So it's like 6,000 instructions versus a lot more. So something's not actually happening. And I also don't see compile stuff, right? So like when we're in the examples and we run, let's go to examples. Let's go back here. Yeah, you can see there's these L files, right? I'm expecting those L files to be generated. Let's do that one more time. JIT, NLC pi, detail, very efficient net. Anyway, I think just being able to see the NLC pi's performance on this and getting more or less things that we're expecting is, unless we're getting fooled by some synchronization barrier, which could be a thing. But because it lines up with our expectations, or at least my expectations, I don't think that's the case. We can get, a good 5-ish teraflops from this particular vector engine. So let's optimize some Tinygrad. So let's go back into examples where we have our things. So let's look at one of these later ones. And so this loop is 16. And that 16 is probably not so good. And the fact that this is 208, you can see there's no V here, so it wasn't vectorized. And in here we're like looking at less than 49. And that's not what you want. It means that this entire thing would just be essentially simplified into one instruction of 49, one instruction of 49, vector length 49, another instruction of vector length 49, and things like that. Do we use 2? Oh yeah, we do use 2 here. And there's these 4 things. And I have to use multiply add. That's pretty much it. Paranoid Polaroid has a good idea. Should we verify if the output is matching? And can't, because it's using random tensors and it's always different. So I don't think we can. But regardless, like what I wanted to do is just verify what is the performance we get in a matrix multiplication with the hardware. Are we able to achieve it with what we have? When it comes to the NLC Pi backend, the answer is yes-ish. Let me do this with the NLC Pi backend as well. Let's see what we're getting. Okay, so this is where it's going to get hairy. How do we figure out where are these values coming from? Where's the 16 coming from? That's a good question. Very good question. But let's find out. So inside of Tinygrad in the code generator, there's the linearizer. It's also interesting how when using NLC Pi as the backend, right, the amount of gigaflops you get becomes limited because you're doing a lot of back and forth. Whereas when you're generating code, you can create kernels that fuse a bunch of operations together to get the calculation, and that just is a lot more efficient. Right? Like you can use more of the register renaming. So there's, I think there are 64 256 element vector registers in the architecture, but I think there are more of those in the actual hardware. So yeah, you kind of want to have as much as you can get, at least as much as you can get away with. Oh yeah, that reminds me, in the GMMM benchmark we were doing, our VEJIT is only one core at the moment, and that should still it's saying 1 point something teraflops, which is too much. We should expect 600 at most, or 500 gigaflops for a single core. So yeah, this is where things get really, really complicated. So let's see. Okay, so we have some enums. Actually, I'm wondering, where's OpenNP? Is there no pragmas anywhere in this code? The renderer. So if you run with the CPU, you notice it's using all the cores. And does that mean it's using it through Python? We're creating two processes. Why? Two loader processes. Okay, so we're just like loading stuff. And when training, just doing like simple stuff. Okay. And I kind of want to not look in examples or extra. I guess the multi-core stuff is happening inside of NumPy. Let's look at those backends again. Okay. If we look at runtime, Clang. By using CPU, we're using NumPy. And then LLVM. Yeah. So does that mean if I put here these 1 to Clang equals 1? Don't have Clang. Okay, Clang. I don't have Clang. I could install it. Yum info plane. Is that old? I'm going to say yes. Okay. And here It's version 5. I think that's also pretty old. This is kind of all we have. So let me do yum install Tinygrad. I should get rid of this any desk thing here. Okay, so we have dev toolset 7 things. Just have to see if that's enough, I guess. There's another thing I kind of wish I also had Debian support for the vector engine. That would make my life a little bit easier. But they only have, Red Hat style support. Okay, so if we list LLVM toolset 7, so if we SCL enable LLVM toolset 7, then do Clang version, we have some Clang. And then if I were to figure out what it was I ran a while ago, yeah, put it on there, paste. We have Clang now, so I'm expected to do stuff. And what I'm looking for is, are we using all the cores when we're in compiled mode or not? Because if we're not, then what that means is all the multi-core stuff is happening inside of NumPy. And that's why the CPU backend can use all the cores. The code that it's generating is just single core. And that would mean that this is going to be incredibly slow if that's the case. It's not looking good, but we haven't actually started, so let's give that a sec. And we're not using the vector engine. Let's just wait for this to come up with a couple of iterations, and then we can see. Okay, 1.8 gigaflops. Verifying HTOP. Yeah, we're kind of like stuck on a single core. Okay, so that explains stuff. Yeah, that explains a lot of stuff. So when we use Clang, we're going to be just using one core. Not ideal when you have many cores. Where is that 16 being generated? Because if we can just, at the very least, look at that 16 and do things that way. Oh yeah, we can force NumPy to a single core with OpenMP numproc. I think. Wish there was an easy way for me to copy URLs from chats, but I can't. Unfortunately. But yeah, 4.545 gigaflops is slower than a vector engine, so there is that. If we put instead of Clang, put CPU equals 1, and then do OMP numproc equals 1, or is it numthread? I think it might be numthread. Numthread. And we can look here. We have a single thread going on. And ooh, you know what? It could also be that, since I'm not sure if this output is correct for the batch size that I'm using. I'll have to double check that. It could be wrong. Yeah, so now we're stuck with just one thread in here. We're getting 2.91 gigaflops, which is half of this, which kind of doesn't make too much sense, but I mean, there's overhead with using NumPy, so I'll just wait for this to go to 20%, because I think in here the first 10% was 1.8, and then we got 4 gigaflops, so 3 gigaflops. That's it's kind of ballpark, I would say, right? Like, let's say that you kind of expect NumPy's kernels to be quite optimized. But they're not going to be as optimized as hand-coded C with Fusion. So yeah, so it looks like we're at 2.93. But then if we set this to 6 or something like that, we kind of expect it to be more than 2. So we have our 16 coming from here. Could be. Another thing is that this is a convolutional network, efficient net. The better test of the vector engine strengths would be in the transformers. So you might want to change things there a little bit. But anyway, let me look for render error. What was the... Yeah, let's just look into CodeGen. Okay, so going to CodeGen, Tinygrad CodeGen kernel. Okay, 16s. We have some 16s here. We have some float 16s. This has local. Not really dealing with that. 3 gigaflops, 50% extra speed for 600% more cores. Not ideal. Let's go here. We can also limit it on the vector engine itself. So I say VE OMP num threads equals 1. And then we use VE git. Yeah, so if you do it this way, if what you're using is using OpenMP, it will limit the number of threads to 1. This has no effect with mparallel, so this could be a way to see things. So here's in thread mode. You can see there's only one thread now. So let's look at how NLC Pi happens on, or how fast NLC Pi works on a single thread. And then we have to decode this compiler. And that's going to be interesting, right? Like you can see some of the examples of the code that it generates through here, right? Where does this 216 come from? I'm not sure. But regardless, we are still chunking it in 4, right? So this should be an 864 length kind of thing. Maybe can I look for comma 4? I'm not sure if this restrict is helping or hurting. Ideally, it should be helping. What restrict means in C is that this does not overlap with this, guaranteed, right? So the compiler can generate code where it doesn't have to assume that it doesn't need to make a copy of one of these first and then copy it in. It can just go, this is always going to be different from that. So that's good. Although in general, like this isn't, so this code isn't terrible given this, right? 216, that's a pretty big vector length. So our expectation is that we are taking, essentially 4 vector instructions of 216 plus a little bit of overhead. So that's not terrible. And it's generating a packed loop because using float, so that's good. But what is doing this? So let's see if we can find in C style that ×4. It's only ×4 here. Let's see 4. Where are we rendering floats? In the render 4 method, of course. So max expert plus plus. When you look at it this way, this looks perfectly reasonable. But we are doing things slightly differently. Let's render store, microps to C style. And what do we have here? Span float 2. Yeah. I think I'm going to need some more coffee to understand this code. I think it's also a good time to remind everyone to follow me on the social medias if you haven't already. It helps the channel. We are like 4 subscribers or followers in Twitch away from like whatever tier they have in the beginning. We only do this streaming in ExpressAI for like, I don't even know why we do it, but we do it, and I think it helps the vector engine community, at least when we do things on the vector engine. And it's a way for us to showcase what we do. So if you're interested in AI or doing AI with strange hardware, give me a follow, and that would be great because it means we can do more stuff. But anyway, so let's get back to that. Yeah, you can see how much slower it is when it's only using one thread. The interesting thing is the 92 seconds per iteration. 92 divided by 5 is 18. We're getting 18 per. I'll have to try that. Yeah, it seems like particularly slow. So if we get rid of that and then do this, we should be doing it in LCPy with all 8 threads, as you can see here. Just capital H to see the threads in top, and you'll see they're all there. And boy, I wish this percentage CPU meant something, but it doesn't. Okay, we have our types. We have runtime. There's some graphs there. CPU. Let's look at the Clang one, right? So the Clang uses this, then it calls as a program stir here. So what we want to see is what calls compiled dot compiler or render. UOps to C style. Okay, so that will produce some stuff. And I hate 2 indentations. It's like I'm too old for that kind of stuff. Yeah, 1, 2, 8 more cores. 1 more gigaflop, half the time. It's kind of weird, you know? Really weird. Let's do the JIT so we can see that going fast. Thread elements. So we have this times 4, 16. This is metal things, right? So we can ignore that, ignore the hip. Then we don't need that at all for that thing. Let me see if I can get some like prints to we'll do some like print debugging to figure out what is getting called and see if we need to, like, ideally there would be you know, there's a C style language. We could have another one. Probably the best for the vector engine is actually Fortran, but I don't think I'm up for creating some Fortran right now. Let's look real quick at Tinygrad code gen. Or no, we want runtime. So go to the runtime and we look at the CUDA. CUDA is our HIP, because I can see HIP devices in the code a lot more. Where are they generating the code in here? Let's hit for linearization. And it's the hip allocator program, which should be here. It's weird, it like takes bytes, so compile CUDA style. Let's look at this one. So this is in helpers pi. CUDA style, type here. Create program is passed to compile CUDA style, which is used. It's just prog, so this thing gets used somewhere. We need to figure out what generates the prog for us. Compile hip is called where? I don't want that. We're using it down here. Compile hip. What's the device? Guess it must be in here. But then what I'm kind of wondering is where's the CUDA code? Let's run the test, the VE test. Cool. It's rm.rf_.l. Okay, let's run test with VEJIT. Okay, cool. We have some code. And if you open up the examples, you can see the 3 different C files that were generated. And this should be simple enough for us. What we have is E33, which is completely inline to that first vector. I should probably show what the VE test does. So VE test does I, then creates this, multiplies it and sums it, and then also calculates the grad. So this creates the I. This should be doing the multiplication and addition. And ideally, this would be calculating the grad of that. I think I have it backwards. This must be calculating gradients. That's calculating or perhaps not. We have data 1, 2, and maybe this is a little too small. Let's up the game in terms of VE test. Let's do a 512i. And then multiply it by 2 in every element. Does that calculation work out? Yeah, it does. Okay. Let's remove the L files, try again, and then look at the outputs. Okay, so here we can see 512, and it is doing these things. This has been completely vectorized, so that's an interesting thing. If statements are not a thing that you can vectorize, like usually, but we do have in the instruction set things called vector masks. And a vector mask, there's vector mask registers and vector index registers. The vector mask register is a 256-bit, I think it's 256 bits. And essentially when the bit is 1, then that vector will be used, or like that element in that vector will be used. And if it's 0, it will be ignored. So essentially what you can do is apply your if statements to a bit pattern, and then you do your thing, and then that will do it that way. Yeah, and you can do it in 32-bit mode as well. So pretty simple. But this does do it. So this is doing this thing, and this is the thing I kind of want to understand. Let's look at the messages. Multiple store conflict data 0. Right? So this could do something, but it can't because there's a store conflict. And I'm not sure if that prevents it or not. It could be that it's just saying, hey, this code sucks, but we're going to do it anyway, and it might not work. Right? That could be what they're saying there, because otherwise it looks like it's vectorized. But it could also be that, well, this thing is vectorized, but then these ones are not, and that slows things down. If we look at the prog inf, our average vector length is 111 for a very, very small kind of calculation. So let's see if we can find this thing. So where in this code can we find this for loop? Let's see what kind of render 4s we have. So if I do pragma, let me see IV depth, like so. Then let's clear, let's RM the L files, and then do this again. Do we see that in these for loops? We do. Okay, cool. So IV depth is not necessary because I've also forced it to do that in my compiler flags. So we don't need to do that. But there are other things that you can do in their pragmas. So let's go here. So let's look at the pragmas. Okay. And if they're not the compiler directives. So you have always inline, atomic, collapse, no concurrent, right? And gather, reorder, inline complete, list vector, and so on and so forth. Now, I think we can do, and this is a crazy thing, we can like change the optimization per for loop essentially. That's pretty crazy. And then we can do parallel for. And that's one I might want to try, right? Like if we, so this, no reason for it to be parallel for, but this one could be, for example. But from what I can see, there's only one render for in the entire in the entire code base. So there's no way for us to, with this implementation, distinguish between the outer loop and the inner loop. What we'd want is to kind of parallelize the outer loop so that the inner loop can be vectorized. V overtake. So we can do V overtake as well. Right now, and we see the overtake. Let me see if that gets rid of that error. So here, we look at multiple sort conflict. That's not going to do anything. And this is not the right level of granularity we want for. It's just one. We can make more, right? Where is this being called? There's a loop. We do that. This is in uops to C style. Print something here. Stop that L. And will that work? Okay, so yeah, we are being called here. And that's kind of cool. 2 loops. Okay, and then KK is append to the kernel. Okay, so that's just string SSA. What is SSA? Prefix U. So that's the op RIDX. SSA, does that mean single store assignment? Let me print these out so I can see. So I want to see C is C, R is R, U is U prefix prefix. Okay, so we can see our C as that, which is a bunch of micro ops. Prefix is that. ACC is 1. I want a pretty print for different things instead. RD print U prefix. Then print C, print R, print U, it's print prefix. And then import that. Can you import that for me? Do you not know what pretty print is? That's not that pretty. About 4. 4 is somewhere, as in the number 4. The thing that is called R. Oh, interesting. That actually failed. That's why it's not pretty. X.numpy. Frequency module is so here it's pretty print.pprint, right? From pprint, I think that should do it. Okay, that should be a little bit better. Okay, so starting from the bottom, we have our prefixes ACC. We have C, which is a dict with int RIDX is 1 and ACC is 1. Then R is a dictionary of operations of the micro ops. And U is loop. These terse names make it feel like I'm decompiling the source code. Render store sizes, whatever. Prefix is always that. If we look at the code's L file, starting at the bottom, how do they line up? ACC 0. So we do have the accumulators here. .513 is being used in the mod. This also doesn't have four things. This one does. So let's go back. It's the first one. It's the first C. Second from the last should be this one. So we have 128, 513. I need to look further back. It's 4. So there's this const 1, 2, 3, 4 that's being used, and then data 0, right? Data 1. It's that. Okay, so I like this one, right? So what's happening here? We are creating this, a bunch of 2s. Oops. Camera went out for a second, I think. Okay, we're creating a bunch of 2s. You can see what's happening is we create val 0, which goes from data 1. And then we put that here and then in the 4 adjacent things. Because of that, we have 512 divided by 4, 128. Completely unnecessary for the vector engine, right? Probably good for other compilers or Intel CPUs. But for the vector engine, we don't want to do this. But it's a good one to look into because it's about as simple as it could possibly get, I think. Okay. So, where's that being called? So we don't need these anymore. I know that. Do we know? We know that the C contains these 1, 2, 3, 4s. The constants. We have data 0, 0, and 1 as globals, and then we have a loop. And our prefix is RDX. Let's put that here to the side. Our IDX is this thing here. And we're doing RDX times 512. That is an ALU, right? I guess that's the address. And then we have a constant 4, or multiplying by, and then 1, 2, and 3 that we're adding to. So that stuff is inside R. Okay. Let's get rid of them now. Okay, and R has these things. And the ALU is this thing. yeah, then we just have like load, loop, and constant. We have the const 1s, 2, and 3, but what is kind of forcing them to happen? Is there a 4 around here? Is my camera running out of battery? It's looks like it has plenty of battery, so that's good. Anyway, where we were at? We were at figuring out why is there 4 of these when there should only be 1, or there could be only 1. Fours, let's get rid of these pragmas. They're not necessary. And that renders the 4s up here. So if we have a loop, we render the 4. And actually, can we just get this? Clear. Let's remove it. Non-type has no object. There's no computation, so we can't do it. But if we do it this way, we get nothing. We have to we do z equals y dot normal y. Something like that. Yeah, I can't do that. I can do this thing, but now I'm gonna have like what kernels that I want. Let's see backwards print. I grab numpy. A bunch of 4s, but now we have 2 kernels to deal with, so that's slightly better. The first one will be a load. Essentially a copy. And this one should be taking 4 things from data 1, 4 things from data 2, and then putting their sum to data 0. Right. Oh, and we have a question about what am I working on? So it's a good time to review, so I might as well. So essentially what we have is a vector engine and this thing. So this is my server with some vector engines in it, and I would like to run Tinygrad on them, and it is running. But the performance is not as good as it should be. And one of the reasons why the performance isn't as good as it should be is that it is kind of decomposing loops into like unrolled things. And I want to figure out what code is causing it to be unrolled like that, and see if I can remove it to see if I can get a better performance from that. And to do that, you essentially have to look at the compiler output and then try to figure out where that is being generated in this code. So this is the Tinygrad code, and it's very terse and not exactly the easiest thing to understand, but that's fine. We'll figure it out. Right now, I've created the simplest test I could possibly do. and it just kind of creates two tensors and adds them together. So I'm trying to figure out if I can find the thing that is generating these 1, 2, 3s, and then get rid of them so that this for loop can just be, you know, up to 512. That should get us 4 times more performance. If it's greater than 4. So this 4 is here, and that's an interesting one. And yeah, and I should also mention what is, what's special about the vector engine. So the vector engine is this thing, right? So it's a kind of, I have some pictures of the card, right? So it's a supercomputer chip that NEC has created, like a Cray supercomputer architecture. And it has the SPU and the VPU. And the cool thing about the VPU is that it can essentially do a loop in a single instruction. So if you have, for I equals 0, I less than 10, I plus plus, and then you do something, well, that doesn't become a loop in the assembly code like you would normally get. So if on the regular Intel, you'd have, your instruction to take the counter and then branch instruction if something, and then it goes back and it doesn't. With a vector processor, you have an instruction that essentially does a for loop in one instruction, and how many repetitions you want it to do, that's, you set something called the vector length register. So if you want to do 10 repetitions, you set vector length to 10, and then you do the vector add, and then you can add anything from, like a constant, or add everything from vector 1 to vector 2, up to 10. And if you wanted to do 20, you just set the vector length to 20 and does 20 instead. The max on the vector engine is 256. So you want it to be, to get the most performance out of this, you want it to be always 256 as your vector length. And because this unrolls into 4, we are doing loops of 128, which is not ideal. We want 512 here. So len vlen is greater than 3 is a pattern I'm seeing in many places. And I kind of wonder what happens if I set this to 256. Or 255. And let's re-render the code and see what we get. Still the same thing, so that wasn't it. Let's undo those. Definitely want to do things one at a time when you're in unfamiliar territory. And there's got to be a 4 in here, right? The render cast. We're doing it 4 times. And then OpenCL language does this. That, that looks sus, right? But we're not in OpenCL land. We're not in Metal land. We're not in CUDA land. So we're not in HIP land. Nor are we in OpenGL or WebGL land. So it's not those. Child count. And go for loops. I mean, if it's maybe it's not defined here, but like defined at a higher level, that could be a thing. So maybe let's find it in the abstraction, possibly. So if we go to Tinygrad features, no. Runtime. Realize, perhaps ops. Realize be in the graph. All right, we can also look at the code by setting debug equals 2. So go here and do debug equals 2. I think it shows us the code that is generated as well. It does not. It just gives us some stats, which is fine. It tells us the function name at least. Should also look at efficient net. Let's do this again. So let's go back to the efficient net with debug 2, see what else we get. And while that's going on, can we possibly see where this is kind of always going by 4s? Someone has an idea, let me know. To see the source code, we need to do debug equals 6. Okay, I'll do that next. Yeah, where in the world could this be? Device. What did I change here? Did I change something in? I don't think I did. Yeah, it's fine. Let's look at JIT. So if we go to the JIT, we have Tinygrad. Let me see if we can see where it is unrolling things. And the main thing is just figuring out where it's unrolling stuff. So rolling it somewhere. Because at least it didn't seem like there was any unrolling happening here, though I could be wrong. It could totally be here and I'm just missing it. Because there is a bunch of these, which makes it seem like that would be something we do, but it's not in range 3 that we're looking for. It's kind of like in range 4. There's nothing there.
Hey. So, I thought I'll join. You hear me?
Yep.
Anyone hear me? Chat? Yeah? Okay. Let's switch to a scene where it's like not me in huge.
Yeah, I switched up my setup to use OBS because it allows me to kind of have
that's
just
why
one
it's like that.
window. Yeah, so kind of special.
yeah. Wonder why it doesn't allow me to just switch the layout to... okay, I can hide myself. I'm fine with that.
Yeah, you just click the thing.
Did you maybe
I
just click the thing the moment that I clicked it, and that's why I thought it worked?
Yeah, possibly, yeah.
Okay. Anyway, yeah. Can you clue me in on what exactly it is you're trying to do?
Yeah, so essentially, looking at the codes here. So we're getting less than 6 gigaflops.
Yeah.
I also did this. So there's this extra folder here. I created a in GMM here. I created a NLCPy GMM here. So if we do like Python NLCPy GMM, we can see that you can get 4 teraflops out of this thing. Right? So that's our ceiling that we should expect.
Okay.
But we don't get that. We're kind of, at least with the Retina net, we're getting 5 gigaflops, which is about 1%. So that's not what we want. So the plan is to, in examples, I have a VE test pi. I'm going to get rid of some of these things. And then
now, if you want to, you might want to try out the state of my work.
Possibly. I mean, like
the big benefit is that you can tell it to keep the source code around. You can then modify the source code as you want, rebuild it, and then rerun Tinygrad on top of it.
That sounds compelling, but at the moment, I'm happy with just finding out where things are happening.
Yeah, okay. Let me tell you about one of the things that is happening.
Mm-hmm.
Because you were looking for... let me tell... tell me, let's go that way first, with which kind of unrolling, what are you looking for? Like,
so
because I've spent hours looking into this, and I have a little knowledge.
Yeah. So
literally
essentially,
a little.
Yeah. A tiny bit of knowledge, you might say. So anyway, I tried to create this VE test, which has something very simple, right? And it generates just two source files, right? So like this one, which still does the 4 unrolling, and then this one, which unrolls 4, but just sets these 2 things to that. So it adds the two things together. So this is about as simple as it gets, and I thought this would be a great thing to mess around with, because I can see this, and it's quite easy to, if I just like go to render 4 somewhere.
Yeah, there are several interesting things in here. One is that it sets fixed loop iterations, which is kind of interesting, but in principle would be the big thing. However, this unrolled stuff that you see in there, that happens somewhere where you wouldn't expect it to.
Yeah, I was like going, it must be happening in a higher level of abstraction, because
can you go to the micro-ops to C style renderer?
Micro-ops. It goes to C style. Yeah, UOps to C style. There we go.
Yeah. That's why I call micro ops. Because a U is literally meant as a mu, as in micro.
They put an actual U in there. But anyway.
Yeah. So in there, let me see. Okay. So in there, you have so once you get to those operations that are being passed to it, it is already unrolled.
Yeah.
And where is it? Okay, I should have kept written notes instead of remembering on my memory. So it was called Global Store, I think. Yes. And the global store is in the linearizer, which is in the linearizer.py file. Yeah. And when this global store is being called with variables, and this is the thing that turns the single variable into those assigns and stuff. So that is the level. The global store is being called, I think, in not too many places. There is one that is being used if there are locals to store, apparently, but we don't have that. Group for reduce is one for the accumulators. And wait, why am I looking at global store? Global load is what I mean. Right. So global load yeah, that one's being used in a few more places. Let me find it again. Reduce up. So anyway, the point is that it is during the linearizer call. When it calls linearize, it turns those variables into this unrolled thing. Yeah.
Why does this say 2.4?
What do you mean 2.4?
Like when printed out this upcast ding, it's just the empty dictionary, so it's not there.
It's yeah, the upcast thing came up when I was looking into it. I honestly don't remember anymore. So the only thing that I remember is that while it does kind of come up, it isn't the source of the thing.
Let's see, what about this source offset? Pretty printed. This is ridiculous. Preprint. Okay, so we have store offset, enable ALU, add. Yeah, so there's 4 things in here. Product expanded nodes, IDX expand. So what is IDX? IDX is IDX. Let's move this up here. And do this down here to see what we got. Why is it taking a long time?
Oh, that's because of me, probably. Because I also I kind of started a thing in the debugger to try to see what the things are. VE node.
Yeah, I was using V node 1.
What do we have? 0 and 2? No.
0 and 1, I'm pretty sure. Could be wrong.
Let me. And which one does it use by default? 1? 0?
0. Should use 0.
Okay, then I put 1 there.
Okay, so IDXs is a variable GIDX0, 0 to 1.
Yeah, exactly. That is. But I think that's not the one that you care about. There's another one that it comes into contact with, or it may be. Take a look at the global load. It could be. Let me check my notes. I was kind of, well, not really live tweeting things. So, let's see. Where did I throw that into? Was that the... Okay, Thursday, yesterday... No. Probably in the random channel. So what did I say when I was looking into this? Yeah, global load. As far as I can tell, going through global load in the linearizer class is what produces the unroll, as it expands a piece of memory into multiple variables. And then more things happen based off that.
And you can see this variable 0 to 3. Like, I have the feeling that's really what's getting at.
Yeah. Yeah, I think that is the thing that is being unpacked.
And there's this IDX small. There's an IDX 4, mod 4, which looks sus. It's the only mod 4 in here.
But it's on the image type, which we're
not using.
We're actually not using, yeah.
Expanded vars UIDX. Doing that. Is there pluses that we are? I'll see a string that render loop.
So,
render loop. How many times is this thing called?
mean, render loop is well, called when we actually well, call it. I think by the time it gets to the point where it's actually calling global load to produce the thing, yes, yeah, then it's already too late.
Yeah.
We should probably find out where it produces that variable and introduce something that produces a loop.
This local is not called, right?
That is a train of thought that I should look into. Because I think that maybe there is something that's possible there. Because it's, I think, the compiled thing.
Okay, so this is probably where it's being done. This render load. Uses pointer arithmetic.
The uses pointer arithmetic thing, I've tried it out. It instead of using data and then in brackets the offset, it will use, well, it will do pointer arithmetic.
Nice.
And it didn't really improve things.
Where in the world is it being hard coded and why? Like, it's so weird.
So I think it is okay. Let's start maybe at the beginning, and that would be in the compiled class. And there we can kind of see there is a synchronize, a to program, and they get linearizer. The to program method calls k.linearize on the linearizer and then renders the source code based on the ops. And the ops are in the linearizer. And if we look a little bit further down, we also see, let me find a thing where I can actually see something, because my Twitch stream just dropped. I was kind of watching what we're doing through the Twitch stream. Anyway, so in the device.py file, at the end, like the very last line, that one has def get runner self on an est. And there you have then self to program with self get linearizer with est. So what I'm thinking is that we should probably start there and see whether the abstract syntax tree that we have is actually, is this something that is already not useful, or is it something that we can use and maybe apply our own thing or do our own
Mm-hmm. Mm.
kind of special linearization. It's interesting, so because the ST or the EST, it literally starts with ops, like it's a tree. It is well, a tree of ops, like it's literally the syntax tree here. And like I'm trying to figure out what it is doing, or what its structure is. And we have at the top level we have a store. Then we have as it's a child, or as its children. Are there more than one? No, there's one. But as it's a child has the multiplication, which then has a load and a const as children. At least in my case, I'm running the very simple. I think the example that is kind of as the simple example on the documentation.
Let me look at that house real quick.
You probably want to do that in the getRunner function on the compile device or on the VEJIT device. Because the kernel init is maybe not the right place. Actually, now that I'm kind of talking us through it, I think the simpler way to get it is to just set debug to 6. And run it. Because, yeah, it literally prints the thing if you do that. So if you set debug 6, scroll all the way to the top.
Yeah.
Even further. It's like, yeah, there you have it. Store at load mul. So that is the syntax tree. And that is then converted to, well, the other things. So at that point in time, it is still kind of fine. And apparently we get this on debug level 3. So there's an interesting thing. We can set a value which is no opt.
A value that is no opt.
That is an environment variable. We can set that no opt to 1. I guess. And then the linearizer will not do a bunch of stuff. If I understand that correctly.
Oh, interesting. Interesting. That's a very interesting code we got there. One sec. Let's do the efficient net. VEJIT. And we do no opt equals 1. And if we look at the code, we get, just regular 512s here. Did I restore this IVDEP graph?
Apparently.
Oh. Interesting. Okay, so
That
now
maybe is the magic flag, because at least for our thing, for the simple thing, it produced a nested loop.
Yeah, look at that. Double the performance.
Yeah, all those optimizations.
Yeah. Right off the optimizations, get better performance. That's the great thing about the vector engine.
Okay, what are you running?
The
I want to see
efficient
whether I get the same
you have to use
thing. So
one, you
the
should probably
benchmark.
get 9.5 or almost 10 gigaflops.
So that is the benchmark thing, right?
Yeah, the efficient net benchmark.
Yeah. Okay, so let's disable the debugging. I'm going to keep VOMP num threads to 1 for now.
Yeah, from what I can tell, if you use Clang, it only runs on one core, so there is no multi-core anything going on by default. If you don't set
we
anything,
can.
we can do M parallel to kind of get around that.
Yeah, and previously mParallel made things worse, at least for my thing.
Exactly. Same here.
Okay, let's see. Compiling now.
Vector length is still terrible, but we have 8 gigaflops and real, which is better, which is interesting.
Okay, still compiling.
That is interesting. Let me go.
Okay, let's see. What do I get? Yeah, 8.8, 9 gigaflops. Again, still single core. 9.4. And my average vector length was 74. Which is probably because the thing is kind of small.
Yeah.
But it, I guess I should maybe commit this to a different branch.
Yeah, it'd be nice if it was up somewhere.
Yeah.
Let's see. I'm going to try M parallel and then M parallel inner loop and then M parallel outer loop strip mine. And M parallel sections. Let's see if those do anything.
Let's see, what do I have
10.3. Okay, so M parallel is kind of helping now. But I've done all the opposite. Like I went through the compiler thing and just did everything.
Yeah, I have tried to see whether it helps or not.
Getting somewhere here. Let me try M parallel inner loop. I'm not sure if you need to have M parallel and inner loop or just you only want one of them.
I think you may want to have the FOpenMP thing too, because because it is being
is different.
No, you want both, because Avio starts the OpenMP threads for you. And if you use them together, mParallel will apparently use the OpenMP threads.
Oh, okay. That makes sense. Let's put that to true then. Inner loop. Let's give it a couple seconds. Yeah, inner loop seems to make things a little slower. So let's do M parallel with OpenMP on. See how that goes. Yeah, it'd be cool to get a decent performance. I'll be happy with like 100 gigaflops.
Yeah.
Or
I mean, we've made it
terabyte.
it's for EfficientNet. The vector engine is, I think, even single-threaded already now, like what, 5 times faster than the CPU?
Yeah.
I mean, that's not the fastest CPU in the world that we have there,
Mhm.
but
.46, 10.51. It doesn't seem to make too much of a difference. Maybe a small difference. Yeah, okay, so that's good enough for me. Let's do M parallel outer loop strip mine and M parallel. Let's see how all that works. They add kind of like memory overhead.
yeah. And I think we are again...
Particularly these ones. The parallel ones.
Or... yeah, some of them are kinda...
Did we kill the server? Oh, no, we didn't. It was just busy.
Yeah, some of them make the parallelization really slow. Not the parallelization, the...
compilation.
what's its name? The compilation, yeah.
Yeah, you can see it in action. Parallel routine generated, parallelized by 4. Seems to be about the same. No serious difference there. I'm going to try M parallel sections instead of strip mine.
Yeah, let me see. I've got like a rather simple thing.
Mm.
I'm not sure. Where do I have the thing? PS UX. Okay. So we have something running on both vector engines right now.
Mm.
I'm on VE Note 1 because I'm using a single CPU.
Mm.
And you're on VE Note 2 with full parallelization. Okay, so with M parallel, mine should be not any better because I'm limiting the thread count to 1 right now.
Mm.
And I am getting 1.4 gigaflops. Interesting.
Mm-hmm.
So it kind of lost 10x performance. Maybe because it's just threads waiting on each other or something like that.
It could be. Yeah. I also did some VOMP num threads 1 to just double check if we're gaining or losing performance with more threads. Okay, I think parallel sections doesn't help. And schedule dynamic would be useful. So let's try that.
No, mschedule dynamic is something that always crashed it for me.
Interesting. Let me try. There's also mschedule interblock, which sounds, I guess, good. I'm not 100% sure.
Oh, okay. So I have maybe enabled too many things at once. So I've just enabled parallelism and packed vectors. And with those two together, I get an average vector length of 13.
I mean, I have M vector packed as well.
Let's see whether... Okay, let's not change 10 things at once again. Okay, so just impact vector, remove that, kill the cache, press play. So, mostly compiling. I mean, yeah, with using all cores, it's now at like 12 gigaflops. Average vector length 24. So the parallelism should probably only happen if there is enough work to parallelize also. But yeah, removing vector packed actually did a lot.
Interesting. That's unfortunate. Okay, what is it that I had? mschedule dynamic. It seems to have frozen.
Yeah, mschedule dynamic always is kind of, at least when I tried that, it was very weird. Okay, but now that I have a decent-ish baseline, I think I should also check the MNIST performance, because maybe a fishnet is just too small.
Yeah, I'm thinking what you want is something with with large dense layers, if that has it, or you could try transformer pi or something.
I've disabled a few more things, like a bunch of things at once, and now I have only 8 gigaflops.
I'm getting 16 now.
Why?
Yeah.
What?
I disabled M vector packed.
Oh, and you have all the other stuff enabled.
Yeah, and everything else is like literally. I went from top to bottom.
Yeah.
And pretty much, if there was something that was no by default, I turned it on. And
let's see.
Aggressive associative math, matrix multiply, move loop invariance unsafe sounds great for performance.
Yeah.
So, these are something like the vector power to xpilog and square root and vector square root instruction. I think those
aren't they enabled by default?
I think they weren't, or at least that's what I thought.
Because I went through it, and kind of most of the things were already enabled by default in 04.
Yeah, so like for example, if we go here, right, 04, associative math, yes, right, but I don't see move loop variance unsafe. Yeah, that was there, but floating divide instruction, I don't think it was there. And then I didn't see the power to or square root instruction or short loop, right? So yeah, just kind of added instead of like kind of relying on O4, just decided to put everything that seemed more or less reasonable in here.
Yeah, I'm kind of trying to, well, by adding and removing things, trying to figure out what it is that makes things fast.
Yeah.
Or slow.
It's interesting that the average vector length is 23, but the vector op ratio goes up without vector packed. And that could be interesting. So it could be that the effort required to pack the vectors every time and then do the masking and shifting and stuff like that is causing M vector packed to be slower. Even though it does kind of increase the amount of, it kind of slows things down to 10 gigaflops. It might increase the vector length, but then reduces the amount of vector instructions. Yeah, so it's a good start. I wish it was 100 gigaflops. I would be ecstatic for 100 gigaflops because that would be 1 second in iteration.
Yeah.
And that I could do all day.
I mean, you can set... you have too much output at the moment. That works better for my case. Where it's caching the compilation. Because if you set debug to 2, you get this thing that shows you how much gigaflops per function you get.
And that's quite useful. You can, it's like allowing you to skip the F trace for that.
Yeah.
Vector operation. Oh, the average vector length is absolute crap. 13.
Yeah.
Wait, what does vector packed do? The default is N. Allows or disallows to use the packed vector instruction. So, let me try a couple things. So, if I go back to OpenMP false, but do mcreate threads at startup. What does it do?
Then you may want to set OMP num threads to 1. Because Aveo run creates them on startup anyway.
I see. Let me get rid of that we. Let's get rid of that. That. Routine generated. 16 gigaflops.
Okay, let's take a quick look at the beautiful MNIST thing. because there I had not really that good performance numbers previously. So my best previously was I think 30 seconds per iteration.
Ooh. There was also a like serious MNIST. What's that? VGG7 could also, like VGG7 is huge as well, so that might be a good one too.
Okay, let's see. Now it should be done compiling everything. And I should probably restart it to get a proper average.
Serious MNIST. What's in serious MNIST? We have big convnet, whatever that is. But it's mostly convolutions. Was there...
Okay, so on Beautiful
Transformer?
MNIST, it is down to 15 seconds per iteration
Oh,
using a single core.
oh.
And the CPU is 6 seconds per iteration on that model. So still more to get. So let's see whether parallelizing that makes a difference.
Hmm.
I mean, can you copy and paste me your flags? I also want 15 gigaflops per second, because at the moment the ones that I have produce oh, now I'm running it, but I forgot to give it the thing. Okay.
Interesting, having the, like, messing with the batch size in the efficient net is kind of interesting as well. It's been a while since I've trained, like, you know, mess with batch size. Back in the day, that was all you did. It's like, how do you just make it as big as possible until you get the out of memory error, and then you play with it.
Yeah, right.
Okay, so for efficient net, it seems that if you have a 32, you get 15 gigaflops. You have 64, we got like 16.5. I think we have enough memory for either 96 or 128, so I'm going to try that. But the average vector length doesn't change. That's the interesting thing.
Oh, nice. On the Beautiful MNIST, it does make a difference. Allowing vectorization, allowing it to use parallelization. Without your flags even, I get to 4 seconds per iteration, so 2 seconds faster than the CPU. I mean,
Not
that
bad.
still isn't a lot of flops,
Yeah.
but it is faster, like an actual real thing.
Yeah. Try adding the flags and see.
Yeah.
But yeah, I can get up to over 17 gigaflops with the bigger batch size. In terms of memory, we're still using only 50%. loss is NAND though, so could be meaningless. This that we're getting.
I mean, I get. I mean, yeah, you're supposed to have a NAND loss for like the first 10 iterations.
Oh, okay.
Okay, kill the cache. Press play.
Whatever. I'm going to check out that transformer.
So, one thing that we've learned so far is that enabling optimizations is what produces kind of the problem here. That means what we need to, or if we want to have our own optimizations, we probably want to look at what happens if no opt is not set.
Yeah.
And there is this.
I'm trying to, like, I was wondering what is not you, or what is using the no opt, right?
Yeah, what is using the no opt is in if you go to the device.py file.
Mm-hmm.
That is when you get the linearizer, and the linearizer is what is being used to create the ops that then get turned into the code. And in there it checks whether tensor cores are used.
Mm-hmm.
And whether beam is bigger than 1 or bigger or equal to 1. Now, I have no idea what the beam thing is for. No, while I was talking, I'm already on iteration 19. Like adding all your additional flags didn't really make that much of a difference. I'm still at 4.2 seconds per iteration.
Some input tensors not found. That's weird. So essentially I was looking at a transformer. If I do BE equals 1. So essentially I was getting a transformer at 22 iterations per second with VE JIT, and with VE I can get 2.
And on CPU it doesn't work?
Yeah, and then on CPU it didn't work.
That's weird. Okay.
Yeah.
Can you set it to... No, touch probably doesn't work properly. Or is it installed?
Yeah, it's not installed. I can do Clang. Clang is a thing. I fixed that. Okay, so B is whatever. We can do Clang equals 1. Nope, I didn't like that. Oh, right, because I have that V overtake. I need to remove all the pragmas, which I should try removing anyway, because they shouldn't be necessary.
Let's see if I try to run the transformer on my thing. Let's also clean up the caches first. Well, I'm still wondering, what does the beam thing do? Because if beam is... then it has tensor cores. If you use tensor cores, else H. And then it produces a new linearizer. And
okay, so we get 4 iterations per second on CPU with Clang. But you notice it is just 1 core. So if we were to expand that to the 12 cores that we have, it should be 48 iterations per second. Ideally, right?
no, wait. What are you doing? I wasn't paying attention.
I was running Transformer with Clang.
Yeah.
And get 4.2 iterations per second, which is
I get
slow. And if we do VE JIT equals 1 and let it do its compiling thing, and we get 20 something, which is pretty big leap, 10x.
Let's see. On a single core, I get 4 point something iteration. Let's go 8 cores. And I'm running on, I think, the slower VE.
If you're running on VE1, you should be on the faster one.
Oh.
VE0 is the one that's old and it's missing a cover.
Oh, I see.
For whatever reason. I have another one here and I just need to go to the data center and install it.
Okay, so I'm running at 14 iterations per second. Pretty much exactly. Sometimes 14.2.
Yeah, but that's kind of cool. If you look at average vector length is 40, and average gigaflops is 2.8.
I mean, yeah, that's far off from what it could be.
Yeah.
Yeah, I get average length there 41. Megaflops real, I get 3.7.
That's weird. You're having
vector
much the same
ratio. Yeah, I have essentially the same. I mean, I have copy and pasted your things.
I'm trying with vector packed. Seems to be just a little bit slower.
I'm going to try something maybe stupid. And I'm going to try it on the benchmark because that kind of makes sense. So beam equals... No. I have no idea what the beam thing does, but let's set it to 4.
I'll set it 256. But it has does it have no effect if your opt is disabled?
Oh, yeah, it has no effect when the opt is disabled, that's right. Yeah. I should re-enable that. And kill the cache. Run. maybe while I'm waiting... Oh, it crashed.
Yeah, it crashes if you set it.
Memory corruption.
Yeah. What else was there other than Beam?
Oh, interesting. It compiles several test applications. Can you set Beam to 1 and set Beam to 4 and run it with Clang?
Okay.
We'll do some things, I guess.
Yeah.
Okay, so enabling beam search with the vector engine, at least in my case, results in a crashed application.
What does it do?
It appears to create a new... it appears to compile something several times. The test L file. Oh, you know what? Maybe if I set debug to 6 at the same time, I can see exactly what's trying to compile. Okay, let's try. It spits out quite a bit of
image
stuff.
Is useful or not. Like, what is image?
Yeah, that is something. Okay, wait a second. Compile test. Okay. Now, interesting. The test thinks it doesn't spit out. But maybe it comes up with something that is fast and all the optimizations that we enabled kind of mess things up.
The Clang is not really running with Beam equals 4.
Was it just hanging?
Yeah, it's just kind of like hanging there. Oh, now is it running? No, it's still hanging.
Yeah, you kind of see my my thing. Okay, let's see.
Anyway, I'm kind of wondering if this is image. Well, I might try image. So if we do VEGIT, and instead of beam equals 0, we do image equals 1. Does that make any difference? I guess it wouldn't make any difference for the transformer. So it just runs.
Yeah, it's not loading any image related stuff, I think.
kind of interesting that the performance is okay with no opt enabled, or as no opt disabled, I guess, with transformers.
Oh, I found something.
Mhm.
I just found something.
Mhm.
Okay, kernel.py file.
Yeah.
Line 477. MV block
MV
size,
block
MV
size.
threads per row, MV rows per thread. That seems interesting. You see, like 4 at 8 at 8.
And you can just put MV to be 1. What's MV?
Is there some kind of documentation available on the environment variables in Tinygrad?
Of course not.
Why would it? Right? There's the code. Read it.
Just watch the GeoHot's 7-hour live streams. That's the documentation. It's all in there.
I mean, there is a thing called envvars.mg. Beam. Number of beams in kernel beam search. Opt. Optimization level. MV. Not in there.
Yeah, I guess we could try that. MV. So since we see it's either 4, the block size or the rows per thread. So let's see which one it is.
So if opt has local, but that we don't have local, I think. So we can. Yeah, if opt has local, no, we don't. For let's the upcast float 4 images. I think we don't care about that. Group for reduce. Below this line need to be optional and benchmark.
So we make block size 1 and rows per thread equals 1. Does that make it better or worse? You parallelized, you unrolled, you vectorized. Well, that's pretty good to me. Not sure if the other optimizations are good or not.
Yeah. No idea.
There's still multiple store conflicts though. So it's not universal, but I guess that means we need to look at threads per row. Kind of feel like no opt is what we want. It takes a little bit longer to compile with the optimization. At least it feels like that.
Yeah, maybe. Let's see, do I see any... Maybe the right thing to do is to step through it.
Why is my IV tapping over take back?
I don't know. Did you put it back? Did you do too many undos?
Might have done too many undos. Yeah, you still get like data store conflicts.
Okay, so if I got that right, this goes to...
This being what?
Yeah, I'm just okay. Tries to apply tensor cores. Yeah, I'm kind of trying to use the debugger in the remote thing, and it kind of has problems displaying where exactly it is. Year 6? Okay, so... It seems to go into hand-coded optimizations in the vectorizer.
Yep.
And I think I'm going to restart the remote thing. Sometimes it helps.
The VS Code remote thing, you mean?
Yeah. I love the VS Code. I'm using the IntelliJ thing.
Oh, yeah, that one you definitely want to restart it every once in a while. Like, gets into like a weird zombie state.
Yeah, it kind of works. It kind of doesn't. Honestly, I'm kind of surprised that it is as janky as it is. Maybe it is just because the latency to that host for me is really high.
21 gigaflops.
That's nicer. What did you do?
I think this could possibly be due to image equals 1. So 10x improvement. Where's my money, Tiny Corp? So it's so easy. I just had to like turn off optimizations.
Because your optimizations are crap.
Yeah. Although we have to see what it's like on the CPU with those turned off. So I'll do that next. Okay, so we still have a terrible vector length ratio. 767, but the vector op ratio is 92% now, and that's pretty decent. Okay, let's do climb equals 1. Let's see how this works. Last level cache hit ratio being 96.6 is good. Could be a little bit better. Yeah, but now I kind of want to do that training of RWKV. It makes me wonder, does Tinygrad have support for like multi hosts or multi GPUs?
Okay, so it does that upcasting.
Mm-hmm.
Interesting. So I'm kind of just looking at what happens there. And so in order for it to get into the first block where it is using all the MV stuff, it needs to have has local, if I understood that correctly. So I have no idea what. Yeah, the linearizer options should have has local true for it to go into that first big block, which we don't have. So it kind of checks all the other things, and then it goes into the block where it sets unit stride axis mul4. And then it checks whether it is an image. It isn't. That's the thing again. Is an image. There's again.
Apply opt unroll. 4.
Yeah, but it doesn't seem to go into that thing. At least in the one that I'm looking at. Man, how many buffers does this thing have? 7. Okay. Memory buffers, const buffers. Okay.
Don't enroll more than 32. Why not?
We have that. Okay, so and then it is checking for another thing that it then doesn't do. Potentially do more upcasts of non-reduce axis based on a heuristic. Okay. And then they look while the product of some kind of shape is bigger than 1024. So that is not quite at the end.
Mm-hmm. This upcast mid is like, don't upcast mid anything but 4.
Okay, so we
Seems
have
a little-
added something to XB choices. Okay, so we have XB choices, which are kind of a big thing.
Hmm.
It sorts them. And I mean, I think I've set. Yeah, float 4, merging axes. Not sure why it says float 4 there, because this isn't about, small floats.
Oh wow! If you do no opt with Clang, you get 1.34 gigaflops.
I guess
So, yeah.
it doesn't really improve things a lot.
I mean, it does if you for the CPU, right? Like, so if you turn on the opt, it goes from
Yeah, no, I mean
1 to 2 or 3.
The compiler doesn't do a lot of automatic.
Yeah, but NEC's compiler is like beast.
It kind of needs to.
Yeah, it kind of needs to be a beast in terms of loop
Okay, so
stuff.
I guess
cool.
this axis merging is something that I'm not sure whether it is good, but it is something.
Mm.
Yeah, so it is this upcast up.
Mm-hmm.
I think that is doing things. So it has upcasted.
Yeah, it's either upcast, which is like
axis.
line 511 or 520. Right.
The things that are currently going on, at least in my step through, are line 550 to 563. So just a few lines below. Okay, so it has, in my case, done only a single axis upcast so far. Okay, so if full upcast shape is less than 32, it does another unroll. Okay. So we do have upcasting and unrolling in here. So what does apply opt do? Self shift to axis amount and then upcast. Add to unroll. Insert shift to cast. Okay, so an upcast drops the final dimension. And shift to like you know, that kind of feels like it maybe is doing kind of loop merging in that case. Which we can enable or put on loops as a pragma.
Do I have... Yeah, we have loop. Okay, so we have loop collapse, loop fusion, loop interchange, normalize, split, strip mine, and unroll happening just from NCC itself.
Yeah.
So maybe any kind of like loop, and move loop invariance unsafe, right? So yeah, maybe none of that handwritten optimization would really help much.
I'm kind of trying to see oh, why? I mean, the optimizations essentially do the loop unrolling. There isn't, I guess, that much to say about it. It's literally doing loop unrolling.
Yeah.
Because that's all it kind of does in there. As far as I understand it.
Yeah, I guess we can just force no opt when you use the JIT device.
Yeah, that's pretty simple even, because they get linearizer method that's on compiled. Like we can I have it as its own class. In my case, it's rather easy to do.
Let's see. It's a, was that no opt again wants to be in device compile that gets called from helpers. So, I create compile. It's the linearizer. Yeah, in terms of like when I could do that, that makes things a little difficult.
Yeah, I mean, it is. So what you would need to do is instead of defining the VEJIT variable, you can define the class.
Yeah. Okay, but anyway, I would say I'm more or less happy with the performance for now, right? In terms of like how much better it is. So if we just do VEJIT1 no op1 Python transformer pi in a few seconds, like it's doing transformers. So there is a Tinygrad RWKV project. That I want to start from. And then the other one is Tiny RW or Nano RWKV. From Blink to Yellow. Yeah. And one thing you can see is it's just like better and faster. You can get to where Nano GPT was at 200 steps in less than 50. And you don't need a custom CUDA kernel to train it. So I like that. So let me see if we can translate this from Torch to Tinygrad and try to train a model from scratch.
If you have the data, like if you have everything else.
Yeah, I think the data is, you train it on Shakespeare. So you can totally do that. The examples aren't. Yeah, this is pretty decent, right? In terms of performance. Let's set that image equals 1. I don't think it matters, but I'm going to do it anyway. Data. Shakespeare. Yeah, this does open web text. How big is that one? 17 gigabytes. That'd be kind of fun. To produce GPT-2 124M, you need 8 A100s.
I'm looking at some of the functions that it generates for the vector thing. It's weird, maybe. Like some of the functions it just generates are weird. Yeah. Overhead of loop division is too large. And it's yeah, if that thing would be written in a different way, could be a lot better, maybe. It's like accessing a bunch of different points. Like usually we have like data 1, 2, 3. Here it goes up to data 8. And then yeah, produces a complex enough thing that it then writes. I mean, it does at least find the fused multiply add in a lot of places. But I'm wondering whether it really kind of finds all the vector matrix multiplication opportunities that it could have.
That is a good question. GPT-2 run GPT-2.py. And I need to do this thing about RWKV. It's very annoying. Info open SSL. What SSL do I have? 1.02.
Okay, so it doesn't find opportunities for a vector multiply, supposedly.
Hmm. I wonder why not.
I have it explicitly enabled. Yeah, I'm kind of still thinking that maybe to get the best performance, we really need to give it we need to just manually implement the ops, and then it just passes them like the thing to the interpreter. Because
the interpreter
probably
being without using the JIT, you mean?
Yeah.
Yeah, I mean, like, you can argue that isn't that what NLCPy is doing?
Kinda, maybe. Not sure.
If we do transform point by VE is 1. I haven't run transformer with it.
What if?
It's like some of the fusion operations that it's doing are significant, I think. It's not crazy, but yeah, it's good enough, I guess.
I mean, the compiler does a lot of, again, the NCC compiler does a lot of its fusion too.
I think like getting the thing to generate less functions would be.
Yeah, it kind of produces one for each size and kind of specific thing that it needs.
And that is kind of ideal. Doing.
I kind of get, yeah, that's interesting. Kind of in between, kind of while it is going on, through the things, it kinda goes to like more operations per second, more iterations per second, and then kind of drops down on the last one. Because in the while doing the 50 iteration step, it's like at 17 iterations per second, and then it drops down to 4.
On the last one?
I mean, it drops on to 14. It's like not that big drop.
I see.
And this part where it's doing 16 per second, it's like 7.4 for me, whereas it's 11.9 for you. That's interesting.
Yeah, EJ is definitely.
Is
faster
it come again? What is faster overall?
VEJIT is faster overall than just interpreter with an LCPAN.
Oh yeah. Even though it still kind of sits at an average vector length of 41 for me for that now.
I wonder if there's like a lot of small things going on. Actually, I should.
Another thing that maybe is going on is that it produces memory access in a non-ideal pattern. Remember how we got a lot of improvement by doing a what's its name? Not transform, not tilt. The dot T.
The transpose.
The transpose, yeah, that's what I'm looking for.
Possibly. I don't have enough memory to do mixed or do we? It's like 100 gigs. Can't possibly work. It doesn't need all 100 gigs at once. I don't think it works. Llama, can we do... Like what I want to do is something like real sized, and then see what it's like compared to the CPU. And the Llama 2 would be a nice thing. It's like really, really big.
What is this thing even doing? I'm trying to look at the transformer thing. Because it looks kind of weird.
The transformer benchmark, you mean?
The transformer example.
It's an adder type of thing.
Yeah, I mean it's several transformer blocks, one after another.
You do endless scan would be interesting.
Self at key transpose divided by square root of softmax dropout its value.
And save image. Let's see how long it takes to train the scan. Still, it'd be like super small. Probably best to deal with like a Llama 2 7B if you want to get a good idea of what's possible. And then I also learned about the distributed thing in the extras. Seems a little hip focused. But it might work.
I kind of, well, I'm not even sure whether it is an interesting thing or not. But yeah, I've grabbed for the usage of square root in there. And kind of trying to figure out, is there something where we technically could have a lot of benefit, but it's kind of not available to us or something.
I mean, I did enable the explicit like use.
I don't mean because of the square root itself, but to see, because kind of where are we using a square root in a calculation in a transformer? There aren't that many places.
Yeah.
And
Stable diffusion.
My point is, I'm trying to find the code for the few places where we are using it. And second. Yeah, it comes up in a few files. And they are kind of all of the same shape. It's a single for loop where it is accessing some data and doing a multiplication of values, and like there's a calculation on a single value essentially per loop. It does find an opportunity to do a fused multiply add in that case. It does the vectorization. So now that I know which files they are, let's enable the performance output and see what it tells us.
Oh, hey, the gas training. But 173.59 seconds per iteration, that could take a while.
Yeah, 14 hours, it says. But yeah, what I tried to do, that is search in an editor, but remotely, has just hung the remote editor. And the interesting thing is, it does, especially for the transformer, it does a lot of tiny operations. It's like, oh, do this loop with 2 like iterations. So this one with 3 iterations. Set that value. Do this 128 iteration loop.
Yeah, 128. But I mean, if that's the shape, that's all you can do. Yeah, like this 32.
Yeah, but the problem is that it probably could do a whole lot more. So I guess my problem is that it probably can do, in principle, there is opportunity for the compiler to create highly optimized stuff that could run very quickly if it would produce more complex methods, or things that call others, so it can then inline them.
Exactly. That's the thing that's
its
missing.
Whole full program optimization.
Yeah, we're missing the ability to inline, because like all of these functions are just called one after another, and that could be the main.
And that means it's like go to the vector engine, come back, go back to the vector engine, come back, go to the vector engine, come back. And it's sure, it most of those things take like a few microseconds. But most of those things on the CPU are like in the nanosecond region.
Yeah. Maybe can try running something very simple with ftrace.
And maybe the not the MNIST, the benchmark thing.
Yeah. Do benchmark with count just being 1. No, that size 8 is fine.
No, up to 0. Yeah.
I think there's to do ftrace. Usually you need to do that also in the linker, but I think
I think it passed it to both.
Yeah, I think it will deal with it, no problem. Let's see, what does it look like from the ftrace perspective? Yeah, interesting. Okay, ftrace. Trace that out. What? What did I do wrong? It's a binary file, right? Yeah.
Yeah, I never remember how to use ftrace. I have always to get out the manual.
We do have the manual. Ftrace. You can notice that you want the ftrace user guide. You could also do some annotations when you generate the loops to, if necessary, could be a thing.
Yeah, technically we can.
Yeah, that's what I thought was curious. Illegal analysis information file. What's wrong with it?
Does it have like some kind of no? Maybe it's the ftrace is too old or something. Maybe you need to use the ftrace from. Isn't there like a VE3 or so folder?
Yeah, but I'm using VE2. Yeah, I have the folder, but because we have only normal VEs, then yeah, it's not. There's nothing in it.
Ah, I see.
Maybe let's try that again.
Wait a second. Can I scroll up a bit?
Hmm?
There was something about fopenmp and ftrace. When executing a program on, if shared library is created with compiler option fopenmp or mapl is linked, the program analysis may be displayed.
That could be a thing. Trace. Okay, let's disable in parallel. And fopenmp is disabled. Yeah, it's not a big deal. Not a huge deal, at least. Oh, can't read that file at all. Interesting. Oh, I guess we can't know what's going on. No clue why, but it probably has to do something with LCPy stuff. Although now is a good chance to run this benchmark.
I'm kind of I'm in the middle of pushing my version as a branch,
Okay.
so you can
give it a try.
Get it too. But where do I have pushing stuff from a server is always a bit of pain. Here you can't. Now I need my phone and I have no idea where I left it. I'll be right back.
Okay. Interesting. Without M parallel, we get 9.25 picoflops. PEOMP num threads equals 1. I have a feeling it should be a lot less than 9 gigaflops, but we'll see. Anyway, we have these 300 lines. So RWKV is big. What do we get? 9 gigaflops. That's interesting.
Okay, I'm back.
That is interesting. What if I do 4? So what I'm doing now is a little experiment about 4. So the VE kind of has 8 cores, but it's really more like 2 groups of 4. So it could be that the overhead of the 2D mesh is a little bit higher for these other ones. So if we just limit it to 4, it might run slightly better.
I mean, I get almost the same performance with just 1.
Yeah, it looks like 4 is slower than 1. It's a little weird. Anyway, this is 400 lines. But that's not all RWKV. RWKV stuff is. Let's look at that. So, the channel mix is necessary, and time mix is necessary. That's pretty much it. 12 gigaflops with batch count 8 can be heated. Like 2 threads. I'll go here and blame, and we can see the differences. And then we want this class. That's interesting.
Again? What's interesting?
The 2 threads is getting 4 gigaflops on batch size of 8.
And what was one thread?
It was like 8. Or is it because I have mParallel enabled, which has some overhead?
Yeah, having mParallel enabled can... Yeah. Having it disabled can be faster if you run on a single core.
Yeah, that makes sense. It's not that interesting. Okay. Yeah, with it enabled, then you kind of see, everyone's kind of, it's in line, right? 2 gigaflops, 1 core, 4 for 2. Sort of makes sense. Okay. Then what does this one look like? So this model 5.1. Tiny. Yeah, that's 16 gigaflops. Which makes sense. Like it scales perfectly fine. Given 1 is 2, so. Kernels. So we forward. Yeah, this is the crazy custom kernel for RWKV. And essentially this one doesn't have that. So I'm going to try and recreate this in Tinygrad. Okay. Okay, so I think I will do that in examples. I'll create a new file. RWKV.py.
Okay, so I'm done pushing stuff.
Okay.
So there kind of two things. One is on the Tinygrad project. It's just a branch. The other thing is the PyVEO thing. That's, I think if you want to just try it out in your branch, it's literally one file. You can also just pull it into it. But you would need to change the imports slightly so that it works with your custom built NLC Pi. Otherwise, I have created a new, currently private PyVEO kind of fork that is based on the Aveo branch of the PyVEO repository, but containing the implementation from NLC Pi in the just VEO namespace.
Okay.
So if you want to try out my thing, I guess the simplest way of doing that, interesting. This branch is 2 commits ahead and 94 commits behind.
Oh yeah, I updated the thing. You can rebase it. It should be fine, I think. I also rebased earlier today.
I mean, it probably doesn't make any difference whatsoever. All you need to do is copy the ops.ve file. Yeah, and probably want to change the... Wait, is it? That looks... Oh, okay, no. Let's see. This thing, show me the commits. Yeah, it is a single commit. ops.veo is the file. And in order to make it work, in your case, it's kind of just from the just the one import line that needs to be changed to work in your environment.
Okay, so like I could merge the VEO branch, and then
yeah, I think so.
so we fetch from upstream 2, and then if I merge master, no, okay, I want to merge.
I can merge it through GitHub if you want.
That works too. Oh. Okay, so we have git merge upstream to VEO. That's the merge syntax. I wouldn't mind getting wrong. I don't want to check it out. I just want to merge it. Branch, master git. Can I merge directly from remote?
I can also just click merge pull request. You can fetch.
You could do that.
Okay, I'll do that.
But why can't I merge here?
Maybe because it is weird. Did you mean upstream 2 slash?
Well, because I was only doing Paul.
But yeah, that now it wants you to do all that stuff. Just fetch because it's on master now anyway. For the Tinygrad.
And root became root sometime in the past. And okay, SCL. SCL label plain LVM toolset 7 bash. And source VM then activate SU change own dash R. Okay, that should fix everything. Status git.
Yeah, git pull should give you.
Yeah.
Okay, now you have. Now you should be able. Well, not entirely. There's one more thing.
See that thing.
It's where everything else is just called ops VEO. You may have to refresh this thing, like click refresh.
Yeah, cool.
Oh, you maybe pulled. Right. You pulled from upstream, not from upstream master. Upstream 2.
Mm. Okay. Having multiple upstreams always makes sense. string 2, and now I should be able to right. There we go.
Now you have it.
Okay, and then I needed what to make it work?
Yeah, exactly that line where it says import VEO. Change that to from NLCPy import VEO. That should be everything for your environment. And now you should be able to run an example with just VEO equals 1. No need to set no opt or anything. Also, the NLCPy enable numpy wrap shouldn't be necessary.
Not necessary anymore.
Are you running any? It should be. There should already be some output. It may be waiting. So if you're running something else,
I don't think so.
can you stop it? Like just Control C.
The device is not actually crap.
Yeah. That's expected. Give
right.
that. Okay. That.
Let's make this faster with 8.
It should be showing up with stuff like compiling this and that. But it looks like it can't get a reference to like it can't the VE project the VE process doesn't get ready for whatever reason. So I guess it doesn't work with NLCPy that way.
Yeah. You just check you break it.
Yeah.
Weird.
Okay. I mean, if you want to try it out anyway, it's not that hard. All you need to do is clone the PyVEO repository that I've created, run the Python setup py for it, and that should be enough. The alternative is to get the reference to the PyVEO. I think you can get a reference to the process of NLCPy.
Okay.
Yep, I guess so. I'll have to check the documentation. Because that is where it's hanging, right? NLCPy starts it, starts its thing. Well, let's see. Close library, unload, flags, kernel, library.
So that's and then VEO. 1. Where? So I see. So NLC Pi is starting up first.
Yeah, NLC Pi is starting up first, and it is monopolizing the entire thing.
That could be me. Because I might have imported it first. So if we go to benchmark.
I mean, we are importing it too, right? We are doing from NLC Pi import VEO. Maybe we need to do a from NLC Pi VEO or import NLC Pi VEO as VEO or something like that.
NLC Pi import.
No, import NLC Pi.VEO as VEO.
Oh.
Maybe that stops it from starting up. But yeah, you can see in the VE top tab whether it has. Yeah. I mean, you could also set. I think it's wherever NLC Pi is imported, might just start up first. You could also do something like VEOMP. Yeah. I think it needs the VEOMP thing, not just VE. Yeah, if you do it that way.
We'll have 7 cores for things, yeah.
And now you can see it produces a bunch of .l and .so files.
Yeah.
And you can check every one of them. They're based on the names of things.
Definitely much easier that way.
And if you rerun it, it will... Oh yeah, right. On rerun. So there are 2 ways this is cached. One is it has the add disk cache annotation from Tinygrad, and then there are the files here. And I typically clear both caches at the same time. So that would be...
how do you clear the cache?
Yeah, let me give you... So, RMRF on the L and SO files. And then it's also a what's its name? Yeah, you RMRF the L and SO files, and then you also remove the Tinygrad cache.
So, where's that Tinygrad cache?
I sent to you on Slack the entire thing that I'm using, but it's in your home folder in .cache /Tinygrad. You have an RMRF without any parameters in there. I mean, that kind of removes a bit more of the cache than necessary, but I think it's fine.
Where are the C files?
They are currently automatically removed.
Oh.
If you look into the file, if you scroll up a little bit, it has builder.clean. That cleans up the C file.
I see.
If you and so that it is like those are the things that I had tested with last. The currently commented out are the ones that you've sent me.
How can prevent NLCPI.EO from doing stuff?
So one thing that you could try
start on a different device.
what is the VE node
The VE node what?
so it has this NLCPI VE node class. So nlcpi.venode.ve, that will produce a VE node device. You can connect and disconnect, can set to use that. Oh, and there is a .proc on it. So, stop. Don't do this.
Well, I was like, what will happen if I do this? This is what I was thinking. Not that it's going to help, but I'm like, wondering.
Yeah, what I would do is use nlcpi.venode.ve.proc. Not here.
Oh.
But scroll down where it's creating the proc. Further, it's on the VE device. Kind of the thing right at the bottom, where it says self proc. Instead of just self proc equals to nlcpi.venode.ve.proc.
See. Proc is equal to VE.
nlcpi.venode. Lowercase, venode dot ve in uppercase. No, just .ve. That's v1,
that's
the current one, I think. Does it do the current one? Yeah.
I think so, yeah.
Yeah, I think it may need to be still a function call.
Wasn't it not a...
the proc is not a function call, but the venode.ve I think needs to be a function call.
Oh.
And with that, I guess it should be fine. Well, it is still waiting. Can you... I mean, it's not going to go anywhere. Yeah. Because it could be stuck on open context. I don't think it should be. But... Oh, Bivu va. Okay.
So it's not.
That is unexpected.
Yeah. Wait, is it in here?
Did you leave anything on top? Okay, if you stop it now, where does it hang? Keyboard interrupt on load library. Huh.
So 107.
Yeah, that. So it gets the device, proc, and tries to load the library. Scroll down. Just want to make double sure that we are not doing anything weird. That means we get the process, we get context. It should be fine. Like that should be literally the same way that the JIT is doing that there. I mean, what we can could also do is, if you really want to try this out, just to without NLCpy, install my version of PyVEO.
What do I have?
I mean, you can.
That was a PyVEO?
No, it's just called VEO, but it doesn't work on this machine. Like if you just pip install it. Yeah, pip install is with PyVEO, but again, it doesn't just work.
Why doesn't it?
Py-VEO.
Oh. PSUtil.
I mean, yeah, you can also pip install PSUtil. The problem is as soon as you try to create a process.
So if we go back here.
Or no, not even a process. It's as soon as you try to get a context. Yeah.
Actually, proc. Because they added it?
Wait, scroll down all the way to... we need to change this back.
Yeah.
Okay, now we can scroll up. There it is. VEO device has no attribute contact. Scroll up a little bit more. That is kind of a follow-up error. It's the list index out of range thing. That is the problem in there. And they do have a issue They do have an issue there in their GitHub. But like literally about that, and no one has taken care of it.
I see.
Like not even acknowledged anything. So that's why I've kind of ripped out the VEO of NLCPy and put it into kind of its own thing.
Let's see.
But because I'm not 100% sure about the license for it, even though like in everywhere it says like NLCPy license, redistribution is allowed. I mean, I can make the repository public if you think that's fine. And then I think you should be able to do a pip install of that.
Yeah, I think that should work. I mean,
But
it's
you
on
can
GitHub
also
anyway.
like, yeah. Okay, so I'm going to make that public. Change visibility. Change to public. Yes. Okay, so expressai/pi-veo is public now.
Pip install.
It's git plus I think
Git plus.
HTTP. And
Is it pi-veo?
yeah, pi-veo. And yeah, I think I'm not sure. So when I was building it like directly, I had to pass it. So when I was running python setup.py, I had to pass it use Siphon. So minus use Siphon. I have no idea whether pip install can do that. But you can do a clone and
yeah, I don't think you can do that.
oh, it's dash install option.
Oh,
Install -option equals to, and then or like that, I guess that works.
yeah. It's a good new thing.
Oh, cool. So now let's see whether things work or whether it runs into you're not in the right folder.
Yeah, it's right.
And as you can see, it's not rebuilding everything.
Yeah. That is nice. If we set this to 128, we should also get to 20.
Yeah, now it's recompiling a bunch of stuff because it has never heard of passing an iteration number to anything.
Yeah.
Now that's one of the reasons why I think going with a interpreted approach where we just get like the big arrays may be a better approach.
Possibly. But like, even CUDA kernels It's like part of that 500 megabytes of binary is just a bunch of static implementations of functions of popular models. So
that's true.
like these things aren't, they're dumb, right? Like they're not that smart. So it's probably not, it might be harder than expected to get it to work faster. And 16.92, which is interesting because then if we do the Egypt as well,
Have you no opt equals 0 again?
Not really. No opt equals 1. There you go.
Oh yeah, no opt equals 1. Right. It's disabling something.
Yeah.
Enable the disable.
I kind of wonder if there's any like, I mean, M parallel is okay, but it's not as like smart as going full OpenMP. But the functions we have right now aren't specific enough to go full OpenMP.
One thing that I tried in my implementation but didn't keep was that if the iteration number is high enough, I would only then put a pragma parallel for.
You get like half a gigaflop from my flags, possibly.
Yeah, it's doesn't feel like that much of a difference. Let's see again.
Yeah, pushing the upstream might be interesting because like NLC Pi is available, so I mean I had to build it, but I didn't have to build it. It's only I had to build it because we're using CentOS 7. Or no, we had to build it because it doesn't target 3.9.
The gigaflops look about exactly the same.
Yeah. So it would be nice to upstream this, but like for VEO, we need to run a patched VEO thing.
I mean, we could just ask whether.
Yeah, you could. We could do it.
We could reach out to Erich and ask him to release a new version.
Yeah.
And like, it could be literally the one that I've ripped out of.
Okay. Now this has me wondering though about like using multiple VEs and.
Using multiple VEs is still technically possible. If you scroll down the VE device, it picks up a node number. It could take a parameter. So it could, in theory, use multiple devices. I mean, it could even in practice use multiple devices. I have. we probably want to set like a directory for the compile cache or something like that.
Like something in .cache would be really nice. Where did I see that dist? In a star dot. An extra distant world, right? And there was distributed training. It was distributed. Ibsafar 10 does this, right? And then if dist, it does that. And then we train Safar. Where was the collectives? All reduce. Dist. Web size. How does Tinygrad deal with multiple devices? So get and dist.
So let's see. If getenv dist grads is collectives all reduce TensorCat. That's literally it. And collectives takes a tensor, get and frank, get and world size. World sent.
Interesting. Okay, so gets the hip, and if it also has devices, otherwise it does Tinygrad runtime ops GPU import CL device, and then it creates the different devices, and then dist init OOB world size, and we process append dist.spawn, and then it spawns a process that takes the device and then calls train.
Okay, so we literally should be that far off from being able to do that. I'm wondering whether it would be like if we set VOMP, like if we set it to one thread but use the device 8 times. That could be a thing. Like, okay, if it doesn't parallelize well, but then why should it parallelize well across multiple devices?
We're passing this device here.
Yeah, I think it gets kind of just the VEO name, but you could do a print on it to see what exactly we get.
VEO. So if we
Can you
That
try running
works.
that with like the dist thing?
Yeah.
So just so we can see what device it produces, like what it puts as the parameter there.
This is.
I mean,
you have to do it
maybe we
manually,
can
right?
run. Yeah, we need to do a little bit of manual.
Yeah, if we just do just one, it's not going to do anything, right?
Yeah.
So if we go to the benchmark.
But I mean, for the benchmark, we could try running it. Or the HLB Cipher 10. Could just literally try running it.
Okay. Right. HLB Cipher 10. No module named Tinygrad on Tinylib.
Yeah. So it just doesn't even work. Because that's not an S.
Tinygrad on Tinylib.
Yeah, as I said, it just doesn't work.
Yeah, it doesn't work anymore.
Yeah, probably doesn't work anymore.
Yeah.
Probably they did a refactoring but didn't rerun all the tests or all the examples.
And all it is a set of stuff. Just world that requires lib. It's the raw buffer.
Yeah, I think it's not really worth going into that now.
Yeah.
I'm just looking at the time. It's 3 a.m. for you.
Wow.
So I think you should go to bed.
Yes, I should. I couldn't get the RWKV thing training, but that could be something we do for the next live stream.
I think having gotten it to 15 gigaflops on average, that is.
Mm-hmm.
Yes,
we
nice.
got it to 22.
Or even 22, yeah.
That's
I think
cheating,
we can get better than that even. But I think we would have to figure out a way how we can make it more efficient.
Yeah.
Because
we could just maybe wait. Right, like we could just wait for someone else to do the work.
Yeah, I mean, I kind of think that the interpreted route is the way to go. Because if we look at the way, like, for example, the PyTorch runtime is done, it gets like full on, like full.
But like the thing about
NumPy arrays,
PyTorch, is that it's relying on its own kind of like kernel compiler thing, right?
The PyTorch thing doesn't compile any kernels. It uses its thing.
Wasn't there backend recently in Python?
Oh, I think the XLA stuff isn't enabled by default.
Interesting.
Like I don't think it's compiling kernels on the fly.
Yeah.
But even then, I think that for a lot of things, we probably
C, and also have generated, like a function to do the thing, and have seen the function perform better.
Yeah, but like take this. I don't know. I would probably even. What are you currently running?
The beautiful MNIST.
Yeah, the beautiful MNIST thing. Can you set debug to 2? Okay, because that kind of outputs all the gigaflops per function, so you can scroll up.
No, actually, let's do it with VE equals 1.
I guess VE JIT.
Had a memory.
Yeah, the beautiful MNIST thing.
Right.
Yeah, it runs out of memory with the LLC Pi thing. But what I wanted to do is just to look at how much we
But this should work, right?
Yeah, what I wanted to look at kind of the big functions that we get and how much they do. What are you currently running? Because the output looks a bit different. Is it on CPU?
No, this is VE. This is NLC Pi.
Ah, okay. Because it's just different output from what I'm used to.
What's this microseconds? This is the...
I think that's how long the individual thing took.
Why is it yellow? Took longer to run than to transfer?
No. I think the thing behind it is the total time. And the thing in front is kind of the thing itself.
Yeah. Here you can kind of see, like, it sucks.
Yeah.
In terms of performance.
But if you run the VEO version, you see that some of them do perform reasonably well, actually. Because as I was trying to run this, my IDE crashed. I actually haven't really looked at this properly yet. You can see we have like a few things running at 500 gigaflops. Do we have set? Is this with mParallel or without? Yeah, that's with mParallel.
Yeah.
Okay. I think we'll get about the same result with out mParallel and OpenMP and VEOMP num equals 1. What we kind of see is there are a bunch of functions, a bunch of methods that run with 200. Before we discuss that, can you scroll up a little in the code that we're looking at?
In the code?
Yeah. Okay. No, it does still have the wait result. Okay, so it's not lying to us.
Mm.
So yeah, we see like half a teraflop for some of the functions.
Mm.
A lot are less than that, but we do see some are decently fast. And on the CPU,
this is CPU.
Yeah, on the CPU we see some, or like most of them, aren't as fast.
Mm.
And yeah, I mean, that particular benchmark was already faster on the vector engine by a good margin, I think like 5 times or so.
Yeah.
Maybe we should take a look at the beautiful MNIST on CPU. $80, $90, $70, $33, $80, $60, $70.
I have no opt. No, I don't have no opt.
Yeah, so now do a VE.
I don't have to do no opt with VEO, right?
Yeah, you don't have to do no opt with VEO. It is
already no opt.
Yeah. Wait, what? Are you running beautiful MNIST?
Yeah.
Oh, right. I kind of forgot that we actually got it to be faster on the vector engine than on the CPU.
Yes.
Can you set it to use only one core? And okay, so what we do see is that on a single core setup, it is indeed slower now. Yeah, 23 seconds per iteration. So it does actually get a speed up
From the other cores.
From the other cores in this case.
It's like a lot of memory.
It's like a 5 times, almost 6 times speed up, which is pretty good for multi-core. Like it's almost never linear, so 6 times going from 1 to 8 is pretty good. But I would kind of expect it to get more. Like, why is the best performing thing like 125 gigaflops? Shouldn't it be more on the vector engine?
Yeah, either 300 or 600 depending. But that's assuming that the data set fits in the cache.
Can you scroll up a little bit? A little more? Little more, little more. Yeah, stop. I'm kind of wondering about this this one. 9 gigaflops, 5 milliseconds wait time. It's like 5 seconds wait time on this one function. Can you open the L file for it? R512 784. Yeah. So,
It's partially vectorized.
what does this one do? We can see PUV. So U is unrolled. It has unrolled the loop. Why would that function be slow?
Isn't it just that it's big, like 512 by 784 times 60,000?
But should that really take 5 seconds to do on the vector engine?
That's a good question. Let's get rid of in parallel when we're running on one thing.
You need to delete the caches, or it will not do. It is like that, you know. If there are caches, it will
re-download the
not redo the things. Okay, so it was like R512, 768 and 6,000 or so, right?
Mm-hmm. Yeah, this one. Oh. Yeah, it's this one.
It is right after. Okay, so even now it does take up a while. And can you scroll down to the code that this function actually is? Because so it has RIDX is 0, RIDX 0 plus RIDX 2 times 512. So that is a strided excess.
Mm.
And then the other thing is a strided excess.
Yeah.
This is literally a matrix multiplication, I think. What we are seeing here. That's value times value plus accumulator.
Yeah.
Yeah, that should be like the fastest thing the vector engine can do.
Yeah, not if you write it like this.
Yeah.
And Yeah, if we look at the progin, we'll probably see that. It's probably that this stride that's happening 60,000 times is essentially like causing the cache a lot of problems. You can't prefetch it.
I mean, so would be interesting to see, like, we know kind of hotspot things like that, right?
Mm-hmm.
I wonder whether we could rewrite them. I mean, technically, we've seen rewriting already happen. Because it feels like if it would be, stacked differently,
Mm-hmm.
this could work perfectly fine. Another thing that, now that I'm thinking of it, and I'm not sure how well the NCC compiler picks up on that. Instead of doing pointer arithmetic here,
Mm-hmm.
that is, the plus this plus that. If it was data 1 and then indexed on RIDX0 and then indexed again on RIDX2 times 512.
Yeah, that would. Last time I tried it, that's essentially you have to write this signature as if it were Fortran, and then that's how you can get like the matmul pattern.
I mean,
you
not that signature, but I mean in those lines. 12, 13, 14.
Mm. Wasn't there like a thing for that?
The pointer arithmetic thing.
Mm-hmm.
Painter. It uses pointer arithmetic. You can set that to true if you want to. I have explicitly set that to false. But yeah, you can try it out. I think it doesn't improve things. You need to remove the caches again.
Cache.
Yeah, it's both the cache problems, blessing and problem and curse.
More cache, more problems.
Exactly.
Is there any difference for?
There was another thing. I just noticed we were actually supposed to, end the stream. Already kind of talking about that. And then it's like, one more thing. So, did it produce that kernel yet? Have you looked at?
Yeah, it's pretty much the same thing. any difference.
So there is something about loops that I remember in the manual. So I enable loop fusion here. Loop interchange is also enabled. Normalization. Yes, also enabled. Okay, we don't have any function calls in the loop to strip to do. I think we could try unroll loop complete.
I don't think I've tried that one. So what we want is, was it F? Unroll loop?
Loop unroll complete. This allows loop expansion, complete loop unrolling of a loop whose iteration count is constant. Can be calculated and is less than or equal to m. So we need to set a specific value. So f loop complete is right now 700 something, or yeah, or that.
Yes,
also, don't forget to delete the cache.
Yeah.
Oh, okay, it fails because okay, scroll further up. It failed because of something else. No, in the output. Yeah, compilation failed, unrecognized. Oh, you forgot to put a comma there.
Oh. Happens.
After the F loop collapse. Yeah.
And over there, and there.
It has the expanded on it.
Well, I'm going through.
It seems to make the compiler a lot slower.
Yeah. And if it's making it produce better code, that's fine. G is vector tab.
The default value for this is 4.
So we'll see if that makes a difference in the second run, I guess.
I mean, the individual functions themselves should be the timing of that should already be fine.
I wonder how much of this data is going through over the PCI bus.
I think not even that much. It shows when it's copying stuff to the CPU in this list. So I think so. If you scroll up, you can see that it's like copying something, and no, even before that, there's this copy CPU to VEO. there you have stuff going over the PCI bus.
Hmm.
I mean, every single call for this also goes over to the PCI bus, but pointers, it's like not a lot of data. And there we have a 300 gigaflops thing.
Yeah, 314 gigaflops. That's for doubles, then that's what you'd expect to max. Well, I'm running multiple threads, so. I just wanted to, pull out all the stops.
Yeah.
Do,
I think the unrolling kind of gives it a lot to think, because it sometimes produces like huge things. Okay, so we have our first iteration, so it doesn't have to do things as much often. Yeah, like it shouldn't have to recompile a bunch of stuff anymore. Can you find that file?
Not yet.
Okay.
Or
I guess that. I don't think that's the one, because.
Was it unrolled before?
Well, it was unrolling the inner one, yeah. Okay, but let's see whether we have it in the output. It should be there by now.
Man, this search sucks.
Yeah, it should be somewhere right after an iteration. So if you go all the way down and just find. Okay, so that is now 1.6 seconds instead of 5 seconds. It's not a lot quicker. I mean, 2 times faster is, I guess, a lot quicker now.
Yeah, but we are running with all cores, so makes sense.
I think it was previously even on all cores at 5 seconds. Yeah, it's at 4.8 seconds per iteration. And falling. But yeah, you see all the microsecond operations maybe don't matter as much. But it's whenever we see something in the millisecond range.
Yeah. That one was 13 seconds.
Yeah, that one's 13 seconds. Why?
Pretty big.
Oh, that is the 10,000 times something. That is a. I mean, we should look into it, certainly. But the 10,000 times something, those are the. What's its name? The accuracy calculations.
So not really part of the test or the training.
Yeah. But we should still kind of figure out, why does this particular thing take 13 seconds? Because I don't think it should.
Yeah, but I think that was like a known issue. It's not like our fault. If I remember correctly, there was a comment about the sampling taking a ton of time.
No, it's not the sampling that's happening there, I think. Because we're not doing anything random there, I think. So let's take a look at the L file for it, because that seems kind of the most interesting thing to do. But we also kinda should stop.
Yeah.
Because it's we have a class to teach tomorrow, I think.
Yeah. I'm not the one in charge of the class next, so that's great. Interchanged and vectorized.
Yeah, that is.
They're all very
good.
small.
Yeah, but the interchange thing is probably a good thing. Then we have expanded, then just loops that are not vectorized. So what it has vectorized? Coroutine, unvectorized loop, overhead of loop division, not enough work for... Okay, concurrency makes sense.
Yeah, it's just too small.
Yeah, but then it's literally, again, a matrix multiplication. I think that could be like one of the hand-coded optimizations that our device needs. If we can figure out something, and I think you should go to bed, I will try to figure out something. Maybe it really is just a different way of doing the addressing. That could be literally it, to make the compiler be like, oh, because this is what you're currently looking at. This is the pointer arithmetic way of doing it. In principle, there is also another way, like the repeated indexing thing. I mean, technically it is literally the same. And like for the matrix multiply thing, so F-associative math allows reassociation of operands in a series during optimization loop transformation. When no is specified, the optimization which transforms matrix multiply loops into matrix library call with F matrix multiply is not performed. Okay. We have associative math enabled, right?
Yep. Yeah. Average vector length 26. And that's not great.
And it could be technically a lot better with like a nice vector gather.
Yeah. So next time on the Express AI live stream, we will investigate issues like this and more. And and see if we can make use of our vast vector engine resources to train models to do things that no other model has done before. And long stream this time, 5.5 hours, but we have totally gotten it up to reasonable amounts of performance. Yeah,
better at least it's CPU. Outperforming this CPU.
Yeah, right? Exactly. That's pretty good. And we'll be back next week.
Maybe-ish. It's
Maybe-ish.
Christmas.
Christmas. Or it's the day after Christmas, so we will see, probably.
In Germany, that's the second day of Christmas.
I see. In Japan, it's a school day, so I might be around. Like, it's not special. There's no holidays for Christmas over here, so I will probably be around. So, yeah, I will see you guys then. And until next time, feel free to hit us up in the ExpressAI Discord or on Twitter or anything. Whatever floats your boat, we're happy to interact with the community. And yeah, see you guys later. Bye-bye for now.
Bye-bye.